All right. So hello and welcome to the Open Healthware Conference. If you haven't heard the word healthware before, that is okay because we made it up. We just crammed together health and hardware because we got tired of constantly saying health and hardware all the time when talking about medical devices. So welcome everybody. And let me, thank you. Oop, get on the right window maybe. Let me see. It wouldn't be a tech conference if we didn't have a tech issue, right? So this is just. Am I on the right screen? There we go. Excellent. Thank you. All right. So my name is Alicia Seidel. I am the executive director of the Open Source Hardware Association. And I am here to say welcome to the Open Healthware Conference and thank you for being here because we really aren't anything without you. You make this possible. You are the ones building the hardware. We are just the ones trying to wrangle everybody together into agreeing what the standard is for what open healthware might be considered. And I just want to say an enormous thanks to all of our attendees, all of our speakers, all of our demo tables. Everybody makes this possible. And a huge thank you to the NSF, who is providing the funding for this conference, as well as the workshops. So very excited to have that grant so that all of this work could happen. I'm just going to really briefly talk a little bit about what is OSHWA, just in case everybody isn't completely aware, to get everybody on the same page. One of the most exciting things about my job actually is that we constantly get to go into new industries and new fields of research and sort of introduce ourselves. And so this is kind of what I do all the time in various industries. So the Open Source Hardware Association are stewards of the open hardware definition, and we kind of exist as a sort of umbrella to house the standards that people all agree upon, and sort of keep the principles moving along and moving forward. We're also the certification holder, so if you certify something with OSHWA, we validate and verify that your source is there, that the licenses are correct, and we keep that directory. And then from that, we also collect a whole bunch of data, which is super exciting if you're a data nerd like me. And we also organize community events such as this one. And just to get everybody on the same page about open source hardware, what it means is that you can remix, remake, remanufacture, redistribute, resell, and study and learn from all of that hardware, right? It's really about transparency, it's about sharing, it's whatever kind of verb you want to call it to give something to somebody else, and we just happen to call it open source hardware. So what do we mean by source? This has become a really big conversation in this community, right? Because with just hardware, really what we meant by source was anything needed for somebody to make a copy, right? Which at the time when we first started OSHWA was typically schematics or CAD files or code or firmware, hand drawings even sometimes, recipes. These things are all copyrightable, right? And so I have this example of the University of Wisconsin open source face shield over here. And so you can kind of, get an idea of what those materials might be. But as we sort of grew into this medical space, people had different ideas on maybe what needed to be included in that source. And we have complex medical devices now talking about open sourcing that we haven't necessarily had to deal with the complexities in the same way before. So you all have had lots of conversations about that with us. And Eve is going to share a little bit more about sort of what we have discovered through all of our workshops and conferences with you. And if you open source things, then you can get a certification from us. You don't have to. It can still be open source hardware without a certification. But this is our list of open source hardware projects. We have currently over 3,000 open source hardware projects in our database. What this just means is that we have, verified and validated that you are indeed saying the things that you have put out as open source indeed are open source. There are several benefits that you get with a certification. So you get, we're the third party who is looking over your stuff and saying, yes, in fact, these are the right licenses. This is all, transparent and I can access it publicly. And then you also get, with open hardware, you get attribution and citation with the licenses that open source, have people give attribution to. And then you also become part of a searchable directory. And we are not a repository, and we do not want to be a repository. We are just a directory. So we just link out to wherever your project page is. But I think one of the important parts of having a searchable directory is that we are, not only is it great for the community to be able to find open source hardware more easily and confirm that it is open source, it can also be really useful for patent and trade offices to search for prior art. And we have talked to the USPTO, they're aware of us, at least. And, can't say for sure that they're searching our database constantly, but it's at least a little reassuring that that they know of us and that they know that we're available to search for prior art. So this also creates a provenance, and you get to be part of a directory. It encourages this community collaboration. Like I said, any open hardware that you do, any hardware in general, creates prior art. But we also feel like doing things the open source way really incentivizes innovation, so people can build off of your ambitions and inventions. So, as you know, since we are sitting here, we have decided to delve into this whole concept of healthware. And some of these justifications for healthware was that this community really thought that the current open source hardware certification did not fully encapsulate everything that we needed in healthware. And so basically throughout this process of this National Science Foundation grant, we have been attempting to sort of fix that. What we mostly found was that the hardware document, that the stakeholders really wanted more documentation as part of the source. That was a big deal. And the other really important piece, I think, to remember about OSHWA is that we are not the regulatory body. We actually do not do anything with safety in terms of medical devices. We are only here for the source. So we are only there to check that it is, in fact, open source. We are not making any moves to, pretend to be the FDA or another regulatory body or anything like that. We are not weighing in about the safety of any health or medical device. So with that, I want to bring my colleague up, Dr. Yves Nazan, second. He is going to tell you a little bit more about all the research that we've done in the past 2 years now, and just sort of how we got here and where we're going. So thank you, Yves.
Hello, everybody. My name is Yves Nazan II. I hope you enjoy my voice because you will be hearing it for the next 3 hours or so, because I will be your morning MC. So with that, I'll go and get started. Shout out to us being technically literate. We love to see it. Okay. So I'll start off with just a little bit about myself. So I received my PhD in mechanical engineering from the University of Michigan. Go Blue. That's what I like to hear. And so now currently I am doing 2 postdoctoral fellows. So one here with OSHWA, where we work with the community, with you guys, to help understand what is this thing that we call hardware, or healthware rather, and how can we best connect our community to those that need it, to those that want to be a part of it. My other work that I do, I work at Walter Reed Hospital in basically Washington, D.C., working with soldiers who have different types of amputation and essentially building robots that allow us to assess the quality of life of people with varying types of amputations and lower extremity trauma. And then last but not least, I've recently started an engineering consulting firm with two of my colleagues where we help build, design medical devices. So if you guys have any ideas that you need to help see realized, let me know. And you can find me on this QR code or any of these links. So now that the self-promotion is out of the way, let's talk about why are we here? How did this whole thing start? So originally, COVID showed us that we need a health infrastructure that is both agile and adaptable. And so before COVID, we as Oshawa had maybe less than 10 health-specific projects that were certified with us. But obviously, as the world saw, during COVID and after COVID, we had a drastic increase in health-related hardware due to the pandemic. And so this led us, as Alicia alluded to earlier, to create the term Open Healthware to describe the breadth and depth of projects that people were submitting. And so we define Open Healthware as open source hardware that falls under the umbrella of medical and health-related devices. And so as a response to this community outcry, for Open Healthware, we applied for and received an NSF grant to build out an open source healthware ecosystem that allowed us to focus on the challenges and the needs of our community. And so we started by completing this I-Core program through the NSF, where that allowed us to officially begin to survey our open healthware community, figuring out who they are and what they wanted. And so in this initial exploration, we found a few interesting things. First and foremost, we found that people actually wanted this certification, which is an important part because we are community driven. So we don't want to do anything that the community isn't interested in. But we also found that certification users and people who want to use this certification really value equity and transparency. And so that's something that we've tried to keep in mind throughout this whole process. Also, the people who kind of are in the open healthware space specifically want to help, right? They don't want to do harm, but liability sometimes can be a concern, and figuring out how they can best positively impact the community is something that we found. And then lastly, as we're figuring out threats to our ecosystem, right? People who may not be in line with us, things that really stood out was that we're going to need to think about the standards organizations and regulatory boards, because those might be some of the biggest challenges as we hope to grow our community. And so after our initial survey of our community, trying to get a feel for what is it that people might be interested in, we conducted a workshop series to test some of the hypotheses and ideas that we had gained through that to better understand what the community wanted and how to refine those assumptions to make something useful. And so during this workshop series, which we have pictures here of various workshops going on, both virtual and in person, we were able to talk to people around the world, ranging from hackers to medical professionals and beyond. And so we were able to use a combination of analysis techniques and community engagement to turn the wealth of feedback that we had into actual achievable goals and actionable items. And so there's a lot that we learned in this first year, and I can't and will not name them all, but I think some of the things that really stood out were, like I said, first and foremost, the community wanted a healthware certification. And like I said, as a community-driven organization, community-led organization, that was of the utmost import for us. We also found that a thing that is very important is replicability and documentation. And so making sure that whatever products we come out with really highlight that was something that was going to be key for us. Figuring out that us as a certifying body also need to be very transparent about decisions that we make, the who, what, when, where, and whys. However, noting that we do not guarantee safety. I think that's a key thing. You know, we are not the FDA, nor are we trying to be. And so having that line of distinction was important for us. But another thing that I think we can really use to help our community is, like Alicia alluded to, we're directory. So if you are looking for a project, if you're looking for a maker or a creator to help you, right, we're a place that you can go to hopefully find what you're looking for. And I think that really ties together, because at the end of the day, what we found is that people want community. People want like-minded people. People want other people who care, have a soft spot for others. And so knowing that all of these things were kind of important, we were able to distill those into 4 key themes. So documentation was a key theme, globality, which is another word we made up, which really refers to the international nature of open source medical devices and open healthware. Marketing, right? How do we not only create useful devices, but have people believe that they're useful, have people believe that, oh, there's actually utility here. And then lastly, reproducibility being a key theme. And so we were able to, using different analytical techniques, right, figure out how do we kind of connect these ideas to outcomes. And one of the big things that came from this was presenting all of this at our inaugural Open Healthware Conference. So that originally was in New York at Cornell Tech's campus. And it was a phenomenal time where we really got to garner or collect our community en masse and get together and really engage with each other. And so after year 1, learning so much, we were reinvigorated and really were looking forward to year 2. And so I think what we could describe what we did in year 2 is we can describe it as a triple D approach, right? So we wanted to discover things, we wanted to disseminate information, and then we wanted to deploy actual knowledge products that we created. And so I'll start with discovery. So discovery, when I refer to discovery here, it really talks about how do we continue to discover what it is that people care about, what the community wants, what's important. And so a major way that we did that in our second year was through multiple workshops. So these here are a few of the workshops that we read. So pictured here is the Glia tourniquet. So we had a tourniquet reproduction seminar that was phenomenal. We had makers all across the world recreate this product and tell us their feedback. We had a quality assurance and quality control workshop where we learned what quality processes were important in the open healthware space as we're trying to recreate these devices. We talked about design thinking and the concept of doing design freezes to make sure that if you're creating a device, making sure that it stays at a safe level before you go and push that out to the community. And then another thing that we did was we had an intro for open healthware to talk to medical workers who might not be as familiar with this space so that we can acclimate them to the language and some of the practices of open healthware in the hope of making it easier and intriguing them to join our community. So, after learning these things, right, continue to discover, the next thing was dissemination. And so we wanted to actually put out the information that we learned to the public. And so that happened through a multiple best practices guides, that we called them. So we were talking about, hey, if you're trying to be an open healthware maker, what are some good practices for you? If you hope to replicate, if you hope to talk about quality assurance, if you hope to just be a general contributor, but maybe not a creator, right? How do you do this in an effective way? And so through that, we also had multiple educational guide sections. So what's pictured here is a guide actually that you can find that talks about best practices and talks about how you can really maybe do open healthware in a way that both makes sense for you, but also considers the practices of others. And so we also published some of the work that we did in the academic space. And finally, we have a common language guide, which we thought was particularly useful for those who are new to the open healthware community, because it can be kind of daunting to come in and hear people talking about like, I'm using my pick 32 to do this, and I'm implementing XYZ in Python. Well, maybe that's not what they're familiar with. And so to make sure that we also create an inclusive space, we created this guide. So last but not least, we finally had to deploy or put out the information that we had. And the most important thing, at least to me, that I think that we did was created a healthware certification. So the QR code here actually will lead you to our certification website, which launched as of 2 days ago. And we actually now have our first healthware certification. Woo! And so that, I think, is a really beautiful culmination of all the hard work that the team has put in recently. And so, yeah, we went and rolled out our healthware certification. We have a healthware website that you can also find through the QR code that tells you about not only how to certify projects, but also can give you examples of what healthware is and how you can appropriately document your projects. And then last, we also created an OSHWA policy specifically about where we stand on open healthware, the fact that we are not guaranteeing safety, but we do hope to add positively to our community. And so these are all the things that we've essentially done in the last year and a half, almost 2 years. And it's really encouraging to see what we've done and where we've been, but I want to talk a little bit about where we hope to go. So the most important thing, this was correct as of 2 days ago. I think we actually added maybe 3 or 4 more certifications. So love to see that it's continually growing. The most important thing that we really hope to have to sustain and keep this community is continuing to have people certify their open healthware devices. And so we will be here throughout the weekend. And so if you're interested in doing that, please come talk to any one of us. Please don't hesitate to ask. But we also think that we can continue to strengthen our open hardware ecosystem by sustaining the community that we've made and supporting the needs of that community, but then further expanding our open healthware community by creating, pardon me, local open healthware hubs, both domestically and internationally. So the picture that you can see here are places all across the world where somebody has used the OSHWA certification for a device, and particular areas that we hope to really go in that it's hard to see because they're dark, right, are the Caribbean and in Africa are generally areas that are pretty dark. And so we hope to expand what we're doing there because we know there are a whole bunch of incredibly intelligent creators doing work there, but we want to figure out where's the disconnect and, you know, how can we be of use and of service to those communities. So with that, I will just want to say acknowledge first the team. So not everyone is pictured here. We've have a hodgepodge of people, but this team that you've seen here, plus a whole bunch of the other people who you don't see, have put in a lot of the hard work that allows this conference to happen and allows the Open Healthware as an idea to continue. I also want to say thanks to NSF. And then lastly, but certainly not least, I want to say thank you to you, to our community, right? We did this because it's something that we heard from you all, and we appreciate that you all continue to reach out with us, to continue to engage with us, listen to our emails, not ignore them all the time. Understandable. We appreciate you all for that, because without you, there is no us. So with that, I would say, please stay in touch with us, and you will hear my voice for the next 2.5 hours. Thank you guys very much. And so with that, now I will introduce Alessia Romani. So Alessia Romani is a PhD, has a PhD in design from Politecnico di Milano, and is now currently a postdoctoral researcher at the Free Appropriate Sustainable Technology, or FAST Lab, in Western Canada, or at Western University rather, in Canada. Her research explores the interconnections between design, materials, 3D printing, and sustainability, bridging design and engineering for sustainability through open materials and technology. And with that, we will have Alessia present her work. We should be good to go.
Okay, so good morning, everyone, and hello, or good afternoon, depends where you are following us. I'm very happy to be here and starting this exciting conference, and I would like to speak about one of the projects we are working now at FAST Lab, connected with the Open Healthware Conference and, in my case, Open Design. Just a couple of words about my work and what I'm doing. I'm a postdoctoral associate at Western University in Canada, part of the Faculty of Engineering in the FAST Lab. And if I have to focus on also my background, I did all my studies in Italy at Politecnico di Milano. I studied there industrial design, then design engineering, and later on I focused during my PhD in connecting design to sustainability with a focus on material science and technology and applying it to application, and that's why I'm now currently working on these topics at FastLab. I'm also very recently been part of the editorial board of HardwareX, so one of the main journals connected with open hardware. I would encourage you in case to speak about this later with me if you are interested. And my focus, as mentioned, is connecting materials, engineering, design, and all these words, keywords, in my case, are related with open design, open technologies, and open source. Just a quick words about my lab, FastLab, the Free Appropriate Sustainability Technology Research Group. We are at Western Engineering, and what we are doing is connecting different people from different backgrounds, can be from engineering itself, and in all the flavors of engineering, I would say. So thinking about mechanical engineering, electrical engineering, and so on, but also connecting with other people with different experiences. Can be medical staff, can be other stakeholders that are asking for open source solutions. So that's what we do here. And just here a couple of pictures of our lab through the years. And our approach is basically on having open source as the main core of the main key of our work. So 99.9%, but I would say 100% of our work is open source. So we are relying on things done from other researchers or other makers, and we try to include them in our research practice. And in turn, we are also releasing what we are doing through open source. That's our approach. And in particular, my focus here at FastLab is sustainable materials connected with open design and 3D printing, finding applications. And one of them, of course, is healthcare. You can find us in Canada, so a little bit warmer now rather than the picture that I selected. But still, you can find us in Thompson Engineering Building. And if you're in our area, so the area close to Toronto, I really warmly invite you to keep in touch with me and contact me for visiting our lab. And yes, also, if you are interested in any other works connected with open source and what we are doing, here I leave you a QR code for our page and see better what we are doing. Context, what I would like to speak about is what I am focusing on, and I will show you also what I have with me. I will focus on the case study of the nasometer. I will then show some of the results of this collaboration. It is now at his second iteration. And then I would like to discuss some future works with you and potential opportunities to collaborate. So focusing on the context and gap, accessible speech assessment, nasalities disorders are quite common and can affect speech intelligibility, and they can also lead to different conditions to treat. And in this field, nasometry is a standard practice for clinicians to assess and measure also this problem and trying to keep track through time after treatment. But there is, of course, a gap, and a very relevant one. So devices, nasometers, are usually less accessible or also affordable due to cost or availability. There are specific resellers that are selling them, and it's not that easy also to get some parts. So this led us to define our interest in trying to find something that could also reach remote and low resource settings, and trying also to give one of the only one, I would say, alternative to open source for the speech assessment. Now, there are not so many alternatives. And also, what we would like to focus, having a design approach and a design thinking perspective, is thinking about something that is more portable than what there is now. Usually you connect this device to some laptops or some computers, so it's very located in clinics. And also, we would like to consider its current clinical looking aspect that characterize this kind of tools, and also its sometimes invasive way of using it with a head or using it with handles. So the need that we defined is also having something for a portable and low-cost alternative, and trying to find something that could be comfortable and easily adaptable to different users and different needs for users. I mean, on one side, the user, the patient, can have different ages or also needs, but also the clinical staff that is using. So our aim, especially with the presentation here, is to present something that enables accessible and affordable speech assessment for therapy, considering different contexts, so users, and try to achieve it through the design of the hardware solution we are dealing with, so the open source nasometer. And now I will briefly introduce to you to the M-nasometer, so the mobility nasometer system. This is a project that we started at FastLab, working with some colleagues at Western University, and trying to develop this open hardware tool and validate it through clinical practice, thanks to some fundings coming from the research, the Thompson Endowment, and some support also from the materials from Polymaker. I'm working with some colleagues at the Faculty of Engineering and some of them from the Faculty of Health Sciences and the Ivy Business Schools. What I would like to present to you is mostly the open hardware focus, because one of my colleagues, Niwei Wong, focus on software behind this tool. But in my case, I mostly focus on the open hardware and what we can achieve for the user through the design of such device. And for this reason, what I also would like to give you as a main message is also how the collaboration and how focusing on open hardware design can lead to more accessible tools for speech assessment. And yeah, first of all, I would like also to focus more on how this device works. So the main question now is, how does a nasometer work? And I will start from some references of the literature here, the principles behind a nasometer. So the patient is using the main device that is usually a separation plate, very basic design for this, where we connected two different microphones, one for the nasal cavity, the other one for the oral cavity. And through a nasometric instrument, in this case, can be an interface or can be also a laptop, we can assess what is called the nasalance. The nasalance is a percentage ratio of between the two microphones. So what we can assess through the microphones, so the nasal and the oral acoustic energy, and usually this ratio is giving the predominance of one or the other way, so the nasal or the oral cavity, and leads also the clinician to understand how to prepare the next treatments and how to assess the next sessions with the user. So what we found out is also that checking a little bit through the commercial resellers, we can reach up to $10K USD for the whole set, which is quite an important amount of money, especially for specific contexts. So we really need to think about something more open source, accessible, and replicable solution for also the resource settings. And that's why we focus on the nasometer. So what we have done is developing the hardware. So this is made by the baffle plate and electronics, and we connected it with a software developed by us, a mobile phone app. And hardware is divided in different parts, can be the main baffle plate, and you can see also through here, it's this black part, the main 3D printed part. Then we should connect microphones, in our case, both for the nasal and the oral cavity. And we have at the end one audio interface, in our case, a dual channel audio interface that it's the main connection with the mobile app. And for working on this project, so focusing on the hardware side, what we have done is focusing on the gap design, the requirement that we needed, thinking about the concept we can also try and implement. Then we pass to optimize the 3D printing of our parts and try to understand how to reduce timings, materials, cost from this point of view, trying to redefine and reiterate the design phase, comparing the different use configuration we could achieve, and then also doing some testing performance. So we did some tests with my colleagues at the National Radiology Center for the isolation and the commercial benchmark comparison. So we were testing also some golden standards in field, and we tried at the end our device with some users. So we did a test with some users for understanding also the results we could achieve with the open hardware solution. And then now we are in a second iteration, let's say, where we are trying to refine the user, refine shapes, also thanks for the feedback both from the clinician and from the users. And we will continue to see if we can improve again the design. What I would like to focus on now, it's mostly the result of this first development that we achieved. So the main version that I'm presenting today. And for this, considering the whole system, the hardware part and the software part, I would like to focus especially on one of the parts on the hardware, which can also be connected with all the electronics because it's a reference for the different users, so for the patient that is touching and handling the part, but also a reference for the clinician that needs to understand how to properly use. And last but not least, it's also all the support for the components that will then define the results for the software. So what we were doing was trying to understand and iterate different prototypes, starting from the very rough schematics of how to organize the product, try to understand if we could also fix different handles in different ways. So thinking also about the user and the gesture connected with this device, how to handle, how to keep it in hand, how to use it when touching your face, and also how to assemble the different parts that are that are making this product. And on the other side means also thinking about its manufacturing, so understanding how to print parts without or removing most of materials that we can avoid, so supports, also dealing with some flexible materials for the interface in contact with the skin, and understanding if we could improve or reduce, limit scraps and waste from this point of view. Considering the design requirements, we defined 4 of them, and I will now show you the whole development process connected with this. So the first one, of course, is being low cost, means having a replicable design for us, for common 3D printers, and using also available materials. So we translated it in open design choices connected with the desktop, use of desktop sites, 3D printers, limited number of parts if you could, just to try to optimize also the use of material and the use of filaments available like PETG for rigid part and TPU. Focusing on the output, so on the part, this means for us trying to keep as the main part the baffle plate and trying to keep as much as we could it as a single component where we could also assemble all the electronics on, trying to define some preferred building orientation. As you can see in the central image, we tried also to optimize the use of materials, of supports, and we will also understand if we can define some custom supports and give them a second life, again, for the same project and for the same product. And at the end, we tried also to understand if we could reach some shapes that could be easy to be printed and affordable for people. So asking to really doing a little bit of tuning or no tuning at the end. This because one of the main aim is, of course, to reduce time, materials, and complexity, especially for non-expert users if they have to replicate it somewhere else. The second requirement, so for us, is portability. Try to use this new open design in either inside or outside clinics, depending on the needs for the clinicians. And keep in mind different users, can be different ages, can be different background and context. So we translated it as choice in handheld use, also the use of small analysis instruments. That's why we were thinking about smartphones, for example, and also allowing to swap different holding supports, adding also, if needed, other type of handles or headband. And this means, in this case, to allow, for example, to include some shaped handles in the wall baffle plate, but also thinking about a lightweight solution. So thinking, again, if with 3D printing, we could reduce material and make it more affordable for people, also for long periods of use, trying to connect the audio interface that we were using at the end with a mobile phone directly, and trying to think if we could also use external add-ons for different use, considering also if the users we are connected with need different styles of use of these tools. So if they could handle the main parts, if they need something else to be added, if they need to keep it on their head, different styles. This because we want also to be adaptable for different contexts and uses, still keeping limited parts as main requirement. The third requirement we were thinking about is to be clinically relevant. So the results that we can achieve with this open design should be really used by clinicians in their practices. And this means that the combination between hardware and software should be relevant and comparable to government standards. And for this reason, we choose mostly off-the-shelf electronics. We tried to do some comparison in electronics. We consider also the use of this tool as compatible with current clinical practice. So we considered the current test and we tried to replicate them with our tool. And we also gave the possibility to use existing holding supports already made by third parties. That's why also in the use, as you can see one of our colleagues using and testing the part, we tried also to assess and do different tests with the different electronics. We tried to connect also our tool with existing band head and trying to understand if we could also provide some add-ons or external parts to make this connection possible. And we tried also to think about other alternative adaptation that we will implement in the next time. So trying to adapt those and create new custom handles for different users. This because we would like also to integrate what we are doing with the familiar practices for clinical staff and something that they can really use as an alternative, not to create something that it's maybe not comparable with it, so not used. And as last requirement we were thinking about, definitely being open, as we are here for speaking about this. So both hardware and software should be usable and replicable anywhere. And for this reason, we tried also to rely, if needed, on standard fasteners, on accessible files when sharing all the design, and also allowing for, in the next period, modification in the hardware. So this translated in using some fasteners also for the connection with existing add-ons and thinking how to integrate them in the shape, providing a bill of material with alternative components in some cases, especially for fastener, but also for in the future for some microphones, and thinking about using standard 3D model formats and relying also on 3D projects, so as 3MF file, for sharing what we exactly did for printing the parts and making them replicable just by seeing what we were doing. And this is, of course, because we would like to make it replicable anywhere with standard tools. Thinking about what we have shared so far, for now, we shared everything on OSF for the hardware part. So we have an open source repository, and we shared the software on GitHub. So we really hope that this can be also the beginning for replication, iteration, trials, and implementation, and so on for our project. And we certified also at the beginning of this year this project as certified hardware. We are looking for certifying it for the Open Healthware community. And last but not least, at least from the side, the first paper with the main evaluation of the commercial benchmarking are available online in one paper that we published. So we are still working on implementation on the open hardware, but this paper is mostly focused on the comparison with the real world use and real golden standard use in practice. So if you're more curious on the integration between the hardware and software, I would really recommend to have a look here. And if you're here around for the conference, also maybe speak with me. I will be more than happy to focus more on the comparison with the standard. And last but not least, at least from this first stage, we did a comparison in terms of cost. We tried to calculate the cost of all the components we used and material and timings, and we reached around $135 for the cost of replication. And the 3D printed part could be around 160 grams, especially for the PEG that we used. So this makes it quite portable and also quite affordable if we want to replicate, at least considering a Canadian context. We would like to see if we could also do better for making it even more affordable and replicable in other parts of the world. And future works. So definitely, as I mentioned to you before, this is an ongoing project. So we are still working on refining and improving our part. So in this 7th part that I'm working on, we are trying to optimize the cost, as mentioned before, the material use, trying to compare also the use of different materials for a clinical practice. So trying to see how PEG can last compared to other 3D printing materials. We are thinking about using also polypropylene or using other materials as well, and trying to see if during, for example, maintenance and sanitization, we could keep good results and constant result time. That's why we're thinking about also as a next step scalability. So trying to understand if we could also think at more customization if needed for users in terms of dimension of the part that we need, in terms of way of also handling the part, and maintenance as last option. But again, it's an ongoing project, so we definitely need further iteration and test. And if someone is also interested in knowing more of these, I would be more than happy to speak about this later on. So I mentioned some of the next steps we are working on, a parametric design version for trying to adapt the geometry to different users, more material testing, trying to compare the filaments for further replication recommendation. These can lead to different 3D printing settings or different modification in the shape or making it more like easily reprintable, and also refining the other design, adding the custom accessories, so adding our own headset, handles, but also trying to understand if these are really needed or not. So we would like to have more user feedback also for understanding what is really needed in the practice. And all this work led us also to a further reflection, and I think this can be also good for, in general, all the open hardware community. So our main question during this project was also how to assess the maturity and openness of this kind of open hardware, at least from the openness point of view, maybe less from the technological readiness levels. And this can be also something maybe interesting for healthcare. So what we were working on in another project we did was defining comparison, or at least an alternative to technological readiness levels, thinking about how to define the readiness of open source technology in terms of openness. And what we defined, it's a 9-level framework where we start from the level 1, where we have in the openness initiation, so at the very beginning where we think about making something open, till the level 9, where there will be a complete openness maturity. So we are trying to define also from a point of view of intellectual property and documentation how a project can be assessed in terms of maturity of their open approach. And if I'm doing an exercise now with the nasometer, we can say that we are now more or less at the middle of this scale, where we reached, for example, the full transparency of what we do. We shared all the main document and all the main documentation needed, but still we are in a process of validating. And the next step for achieving, for example, the complete replicability, we should also try to validate this kind of tool with a third-party option. So this can lead also us in next choices and in trying to understand what can be the next step. And if you are more interested also in this kind of work, we just published a paper connected with this framework, so I warmly invite you. This QR code is also connected with the same paper, so I'm also here for any question connected with this. I think there is a lot of potential also for a lot of projects here to understand how to assess how much open technology is open, actually. And after this, I really would like to thank you for the attention and for being here. And if you need any clarification or questions, I'm here with the nasometer here, so we can also check it better, and I can make you also try and see how it is. Thank you so much again. So if you have any question later on, you can follow with me and ask me anything else. Thank you again.
Okay, so next we will have Alex Hornstein. So Alex Hornstein grew up with a soldering iron in one hand and a butterfly net in the other, can confirm. These parallel themes of nature, invention, art, and technology have continued throughout his life. Alex attended MIT to study electrical engineering and computer science, but spent his nights in a hackerspace and his weekends hiking and camping in the mountains, forests, and marshes around the Northeast. Alex has worked for someone else precisely 9 months of his life at an invention lab in Los Angeles. And for the rest of his life, Alex has worked as a serial entrepreneur, starting 6 companies based on inventions that he and his colleagues create. Alex currently lives in Providence, Rhode Island, where he runs an independent invention lab that works on many inventions in parallel, ranging from public health to children's education to filming wildlife. When he's not in the lab or behind a lens, you can find him on the tops of mountains or at the bottom of the ocean, always with his eyes open. And with that, I will invite Alex to come up.
All right. Let's see. Just gonna do one of these. Okay, good. All right. Well, hello everybody. What's that? Right into the mic. Okay, here we go. Hello everybody. So I'm Alex, and today I want to be talking about something I've worked on for the last 4 years now, which is the epilepsy treatment gap, the difference between how we treat and respond to epilepsy in rich versus poor parts of the world. And we're gonna do this with pop culture GIFs as we go. This is a complex topic, and we're gonna use everything we have to keep our focus and attention as we go through it. So who am I? You heard a little bit of the intro. I'm an independent inventor. I learn, I teach, I work in nature, and I'm very interested in infrastructure of many sorts, of energy, of power, and also of care and health. And a lot of these end up coming around how we build tools for our own health and for our own lives. So with respect to epilepsy, when you are born, you toss 2 coins. And first coin is, will you experience epilepsy in your lifetime? And between 1% and 2% of humanity will come up heads on this coin. In America, it's about 1.2% prevalence. It actually goes up in lower and middle income parts of the world because there's a higher increase of head injury. And the second one is, do you live in a place where you have access to care? So if you have a neurological condition like epilepsy, where do you go? And about 1 in 4 people, it'll come up heads for. The probabilistic minds of you will notice that these aren't coins at all. This is a pentacostahedron on one side and a tetrahedron on the other. Forgive me. But this discrepancy, that 75% of the world has a condition that is pretty common in 1 to 2% of the people in that population, and yet they don't have a way to manage that condition. That works out to 50 to 60 million people in the world. This is a problem. And we're going to talk about epilepsy a lot today. And I want to talk about it from 3 lenses, which I've helpfully color-coded for you. So our yellows are the personal lens. Our, let's call it a taupe, are from a neurological lens, and a lavender is from the lens of how we interact with the healthcare system. So we're going to take a trip together, and let's imagine that right now I have an unexplained seizure. A lot of times they say when you're giving a talk, if you're nervous, you should imagine like the audience is naked, but I like to imagine seizing in front of everybody just to calm my nerves. So what would happen next? So from a neurological point of view, in my brain, I like to think about a seizure as this idea. This is obviously a very simplistic model of the brain, but I don't know if you've ever seen this demo of metronomes synchronizing. So you can think of these as groups of neurons that are firing in different ways, and every group of neurons, every network is doing its own thing. And this is done by a wonderful group in Japan called the Ikaguchi Laboratory, and they just started all these guys going differently. And if you look carefully, this is standing on a platform which is free to move side by side. So normally in our brains, networks of neurons that don't have much to do with each other have inhibitory responses that say, don't pay attention to this neuron next to you. We don't care what that one's up to. It's doing its own thing. And this is an example of an analogous system that's had its inhibitory response removed. So if we skip forward a couple seconds, we see that some of these neurons start to synchronize. And they're starting to move back and forth in phase with one another. If this was in a brain, they would also be going faster in the case of epilepsy and firing rapidly. And after a certain number of seconds, everything has synchronized in this system back and forth. Look it up on YouTube if you haven't seen it. It's great. You'll love it. This is similar to what's happening in a brain. Obviously, there's a lot more going on. But what's happening at a neurological level is your nerves are all communicating with each other, and they're firing off and on rapidly. There's 2 big classes of seizure, which we talk about as focal versus general. Focal takes part in one part of the brain. General is everything in the brain. And in this example, let's just imagine that this is a general seizure that I'm having. So the first thing that would happen in a personal point of view is everyone's looking really alarmed. As I was starting to learn about how to show responses of different systems, I was delighted to find that there's an abundance of macaque-oriented healthcare gifts. What's a macaque? It's a type of monkey. So there's like, YouTube is full of these. The internet is full of macaque gifts. So a good Samaritan in the audience would hopefully call 911. And at which point, a couple other things about what's happening in my brain during this time. So we like to talk about these as the ictals, okay? So ictal is a term for seizure. Pre-ictal, you might have a couple seconds of warning that something is about to happen. The actual duration of a general seizure is kind of 1 to 3 minutes, somewhere in that range. And what that means is before the ambulance arrives, I'm not seizing anymore. And then there's this post-ictal window of maybe up to 6 hours afterwards before I return to a neurological baseline, where the signature, the thumbprint of the seizure is written all over my brain. And it looks like occasional firings, epileptiform spikes, that if you were to measure it, you would see that signal. So more of our macaques, so that our paramedics come And by the time they arrive, I'm not seizing anymore. I'm kind of woozy, I'm out of it, and they show up. And at this point, it's worth asking, okay, so great, the paramedics came. What are the paramedics gonna do? So paramedics are, I'm gonna skip back. What are the paramedics gonna do? Paramedics do like 3 big things. They make sure the scene and the responders are safe, they make sure the patient is stable, and then they transport them to the next level of care. So everybody's safe, I'm not seizing on you, you're good. I'm at this point stable and just kind of sitting around and out of it. So now they gotta do the last thing, which is transport me to the next level of care. So to the emergency room, Batman. And then I found with the power of AI, we can make paramedic Robin. We're gonna go all over in pop culture references. This is one of my great joys. Okay, so we go to the emergency room. So we're here in the emergency room. What does the emergency room do? So the emergency room is going to triage, and they're gonna say, well, is he bleeding all over the floor? Do we have to do something right now? No. So after a little while, they sit and they look at me and they say, well, you seem stable. All we have to do is send you off to the next level of care. So to the neurologist, Batman. Robin has graduated. He's moving up in the world. It's great. And I'll be like, Robin, like, are you gonna take me to the neurologist? Then Dr. Robin will be like, no, I'm gonna give you a referral. So in 4 to 6 weeks or 6 to 8 weeks, then you can see the neurologist. And I'm at this point like, yuck. Like what a wretched interaction with the system of care. It's good. I've had a difficult experience, and what's going on here? Like, what does this mean for me? So, you can always tell who the SpongeBob fans are. So I go meet my neurologist, and the neurologist is gonna say something like this. Everyone gets 1 free seizure. Don't drive, just in case you have another one in the next 6 months. But now go home and, mazel tov. This guy's not being crass. This is actually good medical advice for 2 reasons. One is you don't want to diagnose someone as an epileptic and be wrong. That has long-lasting implications on their life and health. And the other is that you don't want to start someone on anti-seizure meds if they don't have to, which is another thing. These have side effects, these have consequences to your health. So he's very carefully making sure that I am, and didn't get Batman fans here. No one noticed this is Dr. Gordon, the police commissioner from Batman. Fine. Anyway, and the neurologist is looking for these 3 diagnostic criteria in the context of epilepsy. I've either had 2 unprovoked seizures, non-psychogenic origin, more than 24 hours apart, or there's some reason to think I'm gonna seize again, or I have an underlying condition that is an epilepsy syndrome, so something that is a root cause of epilepsy. Something which is not super obvious to me before, or wasn't obvious to me at all before I started working on this, is that epilepsy is not a disease, it's not a root cause by itself. It simply means that you tend to seize, and there's like 150 root causes that can have this as a result. So, but this is, and there's many different reasons why this can be the case for you. So 1 unprovoked seizure later, I come back. At this time, of course, it's taken some time for me to get back to the neurologist, so the footprint of this seizure on my brain is gone. So there's no particular reason. They can measure my brain, but they will see totally normal brain waves. I was looking for advice on how to have people take you seriously, and I heard that illustrating yourself as a superhero getting an EEG is one of those ways. But now I've had 2 unprovoked seizures, and so they will say, here you go, you now have a diagnosis as an epileptic, and off I go down into a system of care that will manage this. So again, in this example, I didn't luck out on my pentacosahedron, but on the tetrahedron nearby, where I have access to care for this condition, it's as good as an outcome as I could ask for. And 3/4 of the world would not have a similar outcome. They would have no neurologist to go to. They would just be kind of left, more or less, to deal with this condition. So this is the area that I'm interested in. it's not just me. WHO has a really interesting neurology atlas that they put out every so often, which is looking at the disparity in neurological resources. And what it basically boils down to is a large part of the world simply doesn't have access to neurology as a discipline of medicine. And this is an interesting and hard and complex problem. It has a lot of ramifications for people living in these areas because we all have brains and nerves. Okay, so you mentioned we went through this epilepsy not being the root cause. It's a collection of different things that can cause seizures. Treating epilepsy for about 70% of people who respond to medication is easy and cheap, like 25 cents a day. And diagnosing someone with epilepsy, especially when you don't have neurologists at hand, is hard. So I'm going to add another color category here, which is thinking about this problem from a hacker's point of view. Is what do hackers know about this that people in the field of medicine or in the field of research might not know? And this is my first instinct when I got into it. I was like, oh, I got it. What we should do is make a lot of cheap EEGs. Then the problem is solved. And so you look at it. EEGs, in case you're wondering, they're looking at these little neural pulses on your neurons that come out and can be represented as these like a few microvolt signals on your scalp. And one of the common tenets for anyone who's been in electrical engineering or worked with analog signals is it makes it harder to do this if you put a big wire that's dangling around catching 60 hertz noise from the air. But this is exactly what every EEG in the world does, is we throw lots of like 6-foot-long wires on these microvolt signals. And that makes these things hard. We can do it, you know, we can throw engineering at it. We can put lots of filtering in it. This is precisely how it's worked up till now. But it makes it expensive, it makes it hard. And my first approach was to try to design and build the cheapest EEG in the world, which 2-3 years ago I did. We're not going to talk about that. We're going to talk about why that's not sufficient. So, well, we're going to talk about it a little bit because I got some pictures. The general idea is, can you do an EEG out of a hospital? What does it take to do an EEG at home using phones, using simple sensing, where in the year 2026, we have access to lots of cheap equipment, and understanding that in places that don't have neurology departments, there's no one to give you an EEG in a hospital. No one is trained. No one knows how to do this. So addressing this problem means you have to push and simplify this diagnostic treatment so that it can be done in someone's home or outside of a traditional hospital environment. So it did this. It didn't save the world. Bummer. And it tells me that it's not just, it's one of these cases where you need to go beyond just a device. You have to understand how the system works if you're going to interact with it. And I want to talk a little bit more about that system for the rest of the talk. So one of the fascinating things about how we diagnose with EEGs right now is in America, and this is one of the reasons this isn't going to be the place where we change this system. We have a code in a hospital that a doctor says, oh, I'm going to write an EEG, and it says, you have to cram this test. You have 30 minutes in which you can wire up someone and look for a characteristic signal on their head. And so he says, how do I do this? How do I make this test meaningful? So I looked up a professor from Harvard Med School. I'm sorry to whoever this is, but your picture came up and now you're in mine. Who would give very meaningful advice. You have to do the best with what you have at the time you have. And then the Dr. House advice, of course, would be you should just provoke a seizure. And kind of remarkably, this is what we do. That's the standard of care. You try to cram it into half an hour. So this guy takes Dr. House's advice and flashes lights and makes you hyperventilate. I'm not saying you should do this. I think it's bad. But that's the standard of care. And you're left as a doctor with a seizing patient on your hand if your test is positive. And that's how you confirm an EEG. You're generally not going to see one if you just randomly sample someone for half an hour. So something that neuroscientists have learned in the last 10 years or so, 15 years, is if you just wait. give it a longer window, you will see it. And so this is a really interesting graph from 7 years ago that looked at if you took people who had epilepsy and you gave them an EEG for a long period of time, like let them hang out in a bed for 24 hours, how long does it take before a certain percentage of them have shown a spike? It's popped up intermittently in somebody's reading. And what a takeaway from this paper is after 10 hours, 95% of people with generalized epilepsy, like the one I've been play acting here in front of you, have shown a characteristic spike. So 30 minutes, maybe you get like a certain low level of folks, maybe you manage to hit it. If you wait a little while, you get a very good look at people. Another good reason not to do it in a hospital setting. Another good reason to do it where you're not time bound. And again, looking at what things are like in places that do not have neurological care. We have plenty of doctors. We just might not have specialists in this field. So this, again, from kind of a hacking a system point of view, it raises this question: could you make a regular doctor treat this condition? What does it take to do that? And that's where my thinking has been quite a lot for the last 2-3 years, is what are the tools that make regular doctors effective treaters of this common condition? Treating means you got to do two things. You got to diagnose it and you got to manage it. Managing's easy, so let's talk about it. You can write pretty much everything you need to do to manage epilepsy on an index card. I'm not a doctor, don't write this down in your pre-med notebook. This is not actual medical advice, but this is roughly what they do because I talk to a lot of epileptologists and I write down what they tell me on an index card. But this is roughly it, is once you have a diagnosis, you want to make sure that the meds are working. You adjust the meds if they're not working. If they're really not working for that patient, try some other meds. It's not rocket science. It's just kind of normal medicine. Diagnosing is the tricky part. A couple more things that we've learned in the science, which is taking a while to percolate down into the medicine. A big one in the last 10 years is computational neuroscience has had a heyday, and machine learning models can do as good or better than epileptologists in basically every measurable criteria that we have. It doesn't mean we can replace them. We actually shouldn't. I think with critical things that involve life and health, it's very important to have a person in that loop. Another one is that these devices are more complex than they need to be. So when you go in, we follow a standard which we figured out in the 70s that say an EEG has a certain number of scalp electrodes, and we take all this data. And in the research, people have been asking this question, do you need all that data? So they start pulling channels out and looking at how does that affect the accuracy. And what they find is not so much. You can get rid of a lot of this extra data, which is kind of ossified, is why we have these channels. It's built into our billing system. Somewhere out there, there's going to be a lovely martyr who's going to spend a career fighting to add a new billing code. And I'm very glad not to be that person. But somewhere, someone will do that, and that will change slowly how we do things in America. In 2022, the literature said we could get extremely good accuracy with 4 channels. 2025, we could get as good as just 1 channel, which is remarkable. It tells us we're doing a lot of process and complexity that we don't necessarily need to be doing. We can solve that with analysis rather than collecting raw data. So for the last few minutes that I'm here, I want to just throw a thought experiment your way. What does it take to, let's say you have a year and you go to a population of, let's say, 1 million people. What would it take to find and treat everybody who has epilepsy, who wants treatment, to diagnose and treat them within a year? So I propose that there's 4 core things you have to do. You have to be able to screen the population. You're not going to give EEGs to everybody, but you have to be able to filter out from 1 in 50 people down to 1 in 5, 1 in 10, who you should focus your diagnostic efforts on. We do this right now with something called the ANON questionnaire, which is a series of 8 questions that's been published that gives a very good risk score for how likely someone would be to have epilepsy. This has been used in global health, and what it hasn't been is given with someone who isn't a med student or a postdoc with a clipboard. No one's ever turned this into something which can be done, for example, with a cell phone. No one's turned this into a questionnaire which can be applied using an LLM to converse with people via text. No one has done these things at scale. So there's some simple software that is within the grasp, I just happened to have thrown this at Claude last night. It took an hour. It's not hard. Another one, stop doing EEGs in hospitals. Man, like this was a thing that made sense at a certain level of device and care, and we are in a different era. It's not just what I say. We've been thinking about this. I continue to think about this. I'm not really talking about solutions. I'm more talking about the general systems problem. But devices that you can wear that can measure your skin over a course of, that are comfortable and you can keep on your head for 10 hours at a time are a pretty easy thing to make cheaply. All we're doing is a very simple, like high resolution sampling of a small signal, and we can do that. It's not just me that says this. A whole bunch of people have been making similar devices. So it's not a new invention that one company can or even should own. I actually think this works better when it's a commodity, because this gives you lots of options to get in. Incidentally, this is not the marketing photo I would have chosen. Like, I'm not like an expert in marketing, but like a full-on scowl, like, it's just, you could have chosen anything. Anything, like, final one. In some spots, you have neurologists in one area, generally in richer, fancier areas, and you have lots of people in far-flung areas that don't have access. Now, a neurologist usually isn't the person who gives the EEG. That's usually an EEG tech. And so the neurologist might not even see them. They might do the diagnosis from their computer, wherever they are. And we haven't really built software to enable that, to take data which is collected in point A and do an analysis in point B. And building up things like machine learning to look for consensus among multiple neurologists who can do a review of a EEG scan and weigh in and see if that matches what machine learning model does. It's not super hard to do. It's not rocket science. You can just, it's almost, there's been 15 years of open source machine learning models that have been published here. These are out, it's available. And I do think, it's not just what I think, it's a true fact, is you need a diagnosis for a lifelong condition to come from a human. This is the fundamental tenet of any life science. But you don't necessarily have to physically be there in order to effectively read that scan. And then finally, if we're putting doctors at the point of care who are not experts in this condition, sometimes you need a consult. You need a friend, a Watson, so to speak. And so being able to link neurologists to point of care doctors, so there's an easy place to ask for additional expertise. Again, not rocket science, but it is a thing you're trying to do if you're trying to build out a system that can effectively look into these complex areas. So these 4 ideas are the thing which is between, in my view, where we stand right now and a dramatically more equitable world where this system of health can be applied to people no matter where they live or what they have access to. I think it's a system that we will understand. I call it epilepsy treatment in a box, where you can just drop in a system. It's kind of a spaghetti noodle of a few different pieces of software and a few different pieces of hardware, but that can link together to make a reasonable system for treating this condition, which affects 1 in 100, 1 in 50 people around you. Guaranteed you know somebody who suffers from it. So why isn't this solved? If it's so easy, why isn't it solved? And like all hard things, it's just entropy. And as a student of thermodynamics, I know this basic law, which is that entropy can be solved locally. It can be reduced and brought to order with the application of work or energy. And if this is of interest to you, I would always interested in other sources of work and energy and would love to talk with you. Thanks for your time.
All right. So first and foremost, I'm going to say we have a bunch of food in the back that's still delicious and still there. So feel free, get a plate, pack a plate, something like that. We have plenty of food and we're going to be having lunch. So yeah, make sure to get some of that food. Now, after that, let me. So next, I will introduce Bo Morgan. So Bo received his BS, MS, and PhD from MIT, studying electrical engineering, computer science, neuroscience, and artificial intelligence. He's a champion of free software, hardware, and manufacturing. He has retinitis pigmentosa, a degenerative retinal disease without cure, and is blind with low vision. Bo brings experience from working at small startups and large corporations, including AI Brain, DreamWorks Animation, and Apple. Bo is husband to Nina Morgan and father to Artemy Morgan. And with that, I will set up Bo's presentation. Let's give it up for Bo.
Hi, I'm Bo Morgan. It's really an honor to be here. This is a topic and a conference that is really close to my heart. I knew that I would be speaking about this at some point about 10 years ago. I'll get into some of my personal details in a couple slides. Right now I'm representing Brain Computer Enterprises. It's a company that I've founded about 8 months ago, started working full time. And let's get into it. We are a team. We have 3 directors, and I am CEO, founder, full-time volunteer at the moment. Alex Hornstein, whom you've just heard from, brings a wealth of expertise from the field of open source medical technology, as you've heard, related to epilepsy, but also during COVID, he was sprinting around building ventilators and making sure they could be FDA approved in very clever ways. Did this, fulfilled needs in entire states in the United States. And then once that was resolved, there were no more needs in his home state. He went abroad internationally and met with foreign diplomats and health administrations and fulfilled the needs in foreign countries as well. Just a wide range of expertise. And also we have Ian Collier, whom has been a successful entrepreneur in the sense that he's developed medical technologies in a startup company and ended up being acquired by Medtronic, an extremely large, one of the largest medical supply companies in the world. And so he brings a wealth of expertise related to like the mass production and the global supply chains for proprietary solutions, and sort of how that can inform how our open source technology can learn from that. So really appreciate and benefit from the director oversight of our entire team. Just a bit about the origin story of Brain Computer Enterprises. It's been a story coming for me for a long time. Sort of in retrospect, it's like, perfect. It's like, that's perfect. It just sort of fits together. So yeah, as Eve mentioned, I went through MIT, the Media Lab, got a Bachelor of Science, a Master of Science, and a PhD, all in one swoop, and studied electrical engineering, computer science, neuroscience as an undergraduate, and then in a master's program and a PhD, studied artificial intelligence and computational models of mind and sort of how that relates to the biology and the neurobiology of the human brain. Studied reflective thinking and worked with Ed Boyden on, he's working with optogenetics and like very cool brain-computer interface technologies that are just coming to fruition now in mice with micro LED arrays and brain interfaces that are much more accurate than electrical interfaces. And so really surrounded myself with this great AI neuroscience community, ended up working with a different advisor than Ed, but when it turned into a pure computer science, computational neuroscience project. Took that education and went into industry and worked on a medical startup building educational toys for kids, where we did fMRI studies to make sure that the brain training software we were building that was artificially intelligence based could activate the correct portions of the human brain. There was the, with the social, emotional, self-affirmation sort of things we were doing for children that would potentially be underperforming later in school when they're about 8, 9, 10 years old, the pre-social stage of life. We would train them in the pre-social types of cognition that they would need in a self-affirmative way. And we proved that we were actually exercising the areas of the brain that were associated with self-affirmation, the dorsolateral prefrontal cortex. I am not a neuroscientist, but it's the DLPFC, if I remember correctly. And we worked with Dr. Fumiko Hoft at UCSF, and she gave us her expertise and her guidance in the social and emotional learning in the educational space. And we actually did prove on a couple children and some graduate students that these brain training software were exercising the DLPFC more than like a working memory test case, which was the parietal cortex. And they did a lot of the statistical analysis to help us support those claims. Went on, worked at DreamWorks, as Eve mentioned, doing AI for artistic sort of projects, and went on to Apple to work on things that will not ever be spoken in public. But it was AI related, and they hired me to work on Siri. My job description is public, and I was hired to work on Siri for conversational language interfaces, and so pursued that, saved some money for about 10 years. But at the beginning of that work at Apple, I was diagnosed with a incurable retinal disease. I was actually driving my car down the 101 and ended up crashing it, realized I'm blind. I had been driving cars completely blind, and it's the weirdest thing you don't notice. But apparently I was blind, and 95% of my retina wasn't working. It was just the very center part. So if I stare you in the eye, it's because that's the only part I can see, and then I will move around to your nose and your forehead. But there's about 5 degrees in the center of each fovea that's working, and they told me, you will probably go completely blind, and you probably have about 10 years of vision left. And so I'm like, I'm gonna build an open source solution to this problem that doesn't currently have a solution, because I know there's gonna be a proprietary company out there that's gonna build a proprietary solution, and I'm not gonna like it because I can see that there will be a lot of advertisements and there will be a lot of potential dangers, and I will go into some of the pros and the cons of open source solutions to these problems and some of the closed source solutions to these problems in a subsequent slide. But this led me to save up, do a startup company with that sort of foresight. And so 8 months ago, founded Brain Computer Enterprises, got an amazing team together, and we're on our way. So what are we working on? Sorry, let me try to scan my slide. So yeah, some of the problems with proprietary medicine. So primarily, you just heard Alex, and I think Alex is doing things that I can't understand why he's doing them. It's obviously beneficial for everyone. And from my perspective, I'm being completely selfish. So I will draw this contrast that I perceive that isn't necessarily realistic. But in my case, I see the fastest way for me to get a solution to my personal problem is to work open source and to collaboratively research and solve these problems, because the most inefficient way to do this would be to make a proprietary solution. It slows down research, and we need a lot of research and collaboration to solve the problem. So it just seems like a completely selfishly motivated, optimized way for solving the problem of low vision and blindness as quickly as possible. And when I say solving the problem of blindness, curing blindness, these are problematic phrases because they deal with definitions of what it means to cure blindness. In my case, I have skills in electrical engineering and computer science, and I think building a neural interface with cameras and neural implants, that's a arguably a cure for blindness. It's not fixing any biological tissues, and I think there's details there that it would be awesome if we had a biological fix for these diseases. It seems to be genetic. If we could do some genetic engineering or make it so that it wouldn't occur from a younger age, that would be awesome. This presentation is not about that, but it's about sort of attaching prosthetics and plugging computers into our brains or onto our faces, and living with that as a sort of progress toward understanding, and then maybe that becomes more biological or more aesthetic. I'm not sure what the right word for that would be. So also, there's designs and documentation are not available for proprietary solutions. There's high prices for the reasons of like monopolization of supply chains and intellectual property. I put intellectual property in quotes because it isn't really a thing. There are these three categories of copyright law, patent law, and trademark law in the United States. I'm not sure how much this generalizes internationally, but there isn't such a thing as intellectual property in a legal sense beyond these three different disciplines of law. So we focus a lot on copyright as something, and I won't get into the details of the licensing, but we have a pretty clear strategy for how Brain-Computer Interface Enterprises owns the copyright, and we copyleft our technology in order to try to encourage the open development and research of these platforms without it becoming lost and in proprietary companies. There are proprietary companies, and specifically for the retinal diseases, and just a little bit of the detail about the retinal diseases, there are large blind spots. So if you could put so there's just wide swaths of the retina that just don't work. So you can shine a light on those spots of the retina and you're completely unaware that there is a light there. Actually, they have a peripheral vision test where they'll flash dots of light all over your visual field, and they will say, press this button if you see the light. And it's not like it's blurry or it's dim, it's just not there. And so there's large parts of the retina that are just not there. Or the photoreceptors are not functioning. The ganglions and the other layers of the neural receptors are there. They get disorganized over a period of time if you stay blind in those areas, which is debatably incurable in any simple way. But you can put stimulators onto the retina. There's a company called Argus-2 that developed a neural stimulator that you could put in the retina. I think there's a picture of the Argus-2 on a subsequent slide. But that company went out of business. And so they had these trials with these patients where they installed this stimulator into the patient's eye. And then it worked for a number of years and it had some problems, but ultimately the company went out of business and the patients were calling the phone number and nobody answered the phone. And the doctors didn't know how to work on it because it was all proprietary and they had no third-party companies that could support it. And it actually started to have medical problems in the patient's eye, and it was sort of too dangerous to remove, from my understanding, so they couldn't remove it from the patient's eye because it would damage too much tissue. And so no one was liable because the company went out of business. And so it was literally rotting in these patients' eyeballs. So it's just something I could see 10 years ago as something obviously I didn't want to pursue a proprietary solution for those types of reasons. And we've heard, I think the panel that we heard from yesterday at the Open Hardware workshop, medical workshop, was amazing, and they addressed a lot of these issues, so I won't go into them too much. But the idea that the proprietary companies do go out of business and you lose that technology has so many ramifications for implants. So the benefits of open source are, you know, it increases the speed of research. It improves the manufacturing processes. So if you have distributed processes, you have distributed jobs, you have local manufacturing, it's a better local economy, and it's a more robust supply chain. So not only do you have the products that are local, you don't have to ship them from one country to another country, but you also have more robust supply chains because you can get your aluminum from a local supplier and you can get your other parts from local suppliers. Easier for FDA approval. I've heard stories from, I haven't had personal experience with FDA approval, but I had a colleague that worked with the open source software for diabetes control, for automatic injection software. And from what I understand, he worked with the FDA on the approval of that, and the FDA was telling him that it was so nice to work with open source technology because they could just sort of look at it, read through it, and it was much easier for them to approve that technology. So I think there's potentially a lot of benefits for the open source technology. Right, the light bender. Let me talk about my first product of the day. I will talk about two products. The one that is most inspiring to me when I originally got this condition was everyone's going to be building headsets, and they're going to have displays, cameras, and this was relatively obvious that they were all going to be proprietary up to a point. And there are some open source ones that are available. The ones 10 years ago, you couldn't access any of the camera data. And so I started hacking together prototypes of displays, cameras. There's a photo here of an early prototype where I took a Adafruit display and a forward-facing 180-degree fisheye lens camera and made a little sort of Google Glass 3D printed this little Google Glass headset where I could run a little single board computer to process the video data, display it on the display, and for each eye, I could do the peripheral vision test. You'll see the peripheral vision. Let's see, are there photos in this image? Yeah, on the far upper right, there's a normal blind spot in your, I think it's either your left or your right eye. Every person has a normal blind spot. You can do a little vision test where you move a piece of paper closer and further from your face to see a little dot disappear. This is fun. I did it as a kid. Everyone with normal vision has this blind spot where the optical nerve exits each eyeball. You don't notice it because you don't notice blind spots, even if they're really big, apparently. But this is a normal blind spot up here in the upper left. This is our patient web portal where our headset uploads the data to the patient web portal from the peripheral vision test, and you can see where the blind spots are. There's another form on the web page that allows the doctor to define a prescription. So outline where the doctor thinks the big blind spots are, and then there's an optimization algorithm that will take a mesh and split it up to fit the blind spots. We don't have a lot of work in that area, and I don't have images of that, but basically, if you take this mesh and you fit the mesh within the part of the user's retina that they can see and avoid their blind spots, then you can make an algorithm that takes all the incoming light into the front of the headset, and you can reroute it to the parts of the user's eyes that work, and you can remove all of the blind spots of the user. So what does it mean to remove all the blind spots of the user? I don't know exactly, but what I think it will do, and what I've basically shown very primitive versions of, is that if you do this peripheral vision test with the headset, you will pass it with 100% accuracy. Will you be able to walk around? Sort of. I've walked around with it, but I can walk around basically blind anyway. So I think you can sit, you can use a computer, you can watch TV. You can probably do those types of things. We need higher resolution displays. We need smaller designs. There may be a video here spinning, although maybe the video didn't load. Okay, sorry, we don't have access to the video. There should be a spinning headset. If you click the QR code, or if you go to bce.center, you will see videos of the headset and the Pen-C product that I will describe next. So the evaluation, the prescription that the doctor can design through the web interface, and then the correction. Let me see, this should go to the next page. There we go. So the Lightbender general overview, we have the display, the sensor cameras on the left. We have eye-facing cameras to do eye tracking. My first prototype didn't have the eye-facing cameras for the eye tracking. I just had a cross in the middle of the screen that you would need to stare at, and then we could do the correction based on the fact that it knew your eyes were at 0, 0. But ideally, you have eye tracking so that you can move the light display as the eyes move in the headset. I think this will also be useful in the future for neural interfaces, where maybe you've got a V1 implant and you've got a headset, and you want to send the camera data, which is head-mounted camera, to that V1 implant. You'll need to know where the eyes are looking so that you can feed the correct data into the neural interface in V1 cortex. And I'm a fan of optogenetics and not electrical stimulation, but I'm not a neuroscientist, and it would be super cool to work with open source implant designers in a collaboration that uses sort of this headset eye tracking technology to process the data before it goes there. So the cameras go to eye tracking processors, sends that XY data to a GPU. In our first prototype, we had a single board computer with CPU, GPU all combined. This is actually a different design that we're working on now, where the GPU is separate from the microprocessor, the MCU. And so the microprocessor actually has no access to the visual data. So the visual data goes from cameras through a GPU to the displays, photons in, photons out. There's no data that comes out of this camera. So you can't take photos, you can't take videos. I think it's super important to be really clear about the privacy and security needs of patients with these glasses and the people who are around patients with these glasses. There won't be any photographs and there won't be any videos of those patients, what they're seeing, which includes any of the people around them. And this will need to be certified at an open hardware level, at an open software level, all of those things. And so this is the only thing that loads into this GPU is the prescription from the doctor, and then the MCU has an internet connection, but has no access to the GPU. Okay, so next product. So the Pen C, this is too complicated. I can't build a headset. I've got a short-term runway for this company. I'm self-funding it. I'm going to apply for NSF grants. Super excited for the NSF grants to come back online that I was looking at before. So this September, hopefully those grants come back online. And we're gonna do a different product. We're gonna do something that's simpler, that contains a lot of the same components that will be necessary for the headset, but that I can build really fast and that will be really useful in a much shorter time frame. So what this is the Pen C. It's a pen that allows a blind person to feel visual art. There's a camera in the tip of the pen, so when you move the pen across the surface of a piece of paper, there's a haptic pad that you rest your finger on that will vibrate your finger. Oh, this video we have access to. That's awesome. I was wondering. That's totally my fault. But you can see the spinning headset on the website. So the Pen C prototype allows you to feel line drawings that are black and white and grayscale images. It feels textures and maybe follow the outlines of high contrast shapes. And what I believe this will allow a blind person to do is appreciate visual art, at least in a black and white sense to begin with, and feel where the different textures are. Which I think is completely different from other technologies. Like if you have a cell phone, you take a photograph and you have like an LLM describe it to you. Because this is actually physically interacting with the piece of paper, which allows a blind person to say, oh, here is an intersection of two lines. So I'm gonna put my left finger here, grab my pen, and draw a line from that intersection to another point on the paper. And so the ability to draw and interact with line drawings I think is something blind people currently don't have access to that this will enable. Technical drawings, aesthetic drawings, super fun, right? I mean, that's relatively simple and super cool. And it has the cameras and it has a lot of these things that will be necessary for building the headset. So version 2, maybe just a firmware upgrade of the Pen C, is that if you can follow basic black and white shapes on a piece of paper with this pen, that means you can follow lines of text in a book. And currently you can buy an OCR pen scanner that will allow a person, like a dyslexic person, to scan lines of text in a book and it will read it to you, convert it to audio. And there's many different languages it will convert it to. The problem with this for blind people is that blind people can't see where the lines of text are. So they can't use that pen. So this first version allows you to feel where the lines of text are, so you can follow them in the book, and then we can use the same OCR technology, maybe just a firmware upgrade, that then allows that to be converted to audio via Bluetooth, maybe your Bluetooth headset, or even a Braille display, where you can scan the lines of text with one hand and you can feel the Braille display with the other, and read quietly while you listen to music or have a conversation. In case you don't want your ears filled with robot speech. So this is version 2. Let's see. There's other interesting questions to consider. Color. What do we do about color? That's fun. I don't know. So one idea that comes to mind, someone suggested it, now that they suggested it, it seems obvious to me. Why don't we take the frequencies of the light and convert it to frequencies of haptic feedback? Yeah, that's probably gonna work. We'll have to see. That's so much fun to think about, like how blue is a high frequency, red is high frequency, blue is low frequency. But I'm just sort of, is it the other way around? So yeah, how that feels, and then if you were to invert it, would it feel not right? But that's really an interesting question to me. User interface, the user experience of how to feel color in a useful way for doing art or for doing technical drawings. Just understanding existing visual objects. And PCB design. So if we're a blind community, and we're a blind community of makers, how do we build solutions to our blindness? So let's say that involves cameras and it involves printed circuit boards. Like, how do we read that resistor value? How do we tell what text is on that little black box? Well, we could use a Pen-C. We could put the Pen-C on the PCB and be like, oh, that's what that says. Or these are the colors of this resistor. Or just read me the resistor value. And I already have to use like a little jewelry loop to read my capacitor values. So it's like, okay, well, why don't I just use the Pen-C for that, and then I can not use the jewelry loop. So yeah, there's a lot of cool things that are like maybe not gonna make a lot of money for a big market of blind PCB designers, but I need that to do what I'm doing, and I'm being totally selfish here. But we also have to keep the company going. So these are things for version 2, maybe version 3 for the PCB design. The general overview of the Pen-C is similar. Cameras on the left. There's also an accelerometer on the left because the cameras go, I think, up to 120 hertz. They go from 30 hertz to 120 hertz, but it's not going to be a high enough frequency to get the haptic data we need. So if we have an accelerometer that's over 1,000 hertz, then like I think it's 1.6 kilohertz. We have this accelerometer that we could take it up to. So that gives us Nyquist frequency. We've got 800 hertz of frequency from the accelerometer. So it tells us how it's moving over the visual surface. The camera takes snapshots every once in a while to give us sort of keyframes into that. And then this feeds in, so the camera feeds into an FPGA, which stores it in an SRAM. The microprocessor can ask the FPGA to pull that SRAM for the pixels based on what the accelerometer sort of is doing with dead reckoning within that last camera image, so that we get high frequency data over a relative, it's on SVGA cameras. It doesn't have to be super high resolution, I don't think. And then that goes through an analog filter stage, bandwidth filter, out of the microprocessor, and then there's an analog amplifier as well to give it to the piezoelectric haptic motor. We have a lot of web services as a company. So we have the web page. Everything in our company is open source. And this is sort of toward the goal of like, Amy Goodman just made a movie called Steal This Story, which I haven't seen and I want to see it. But I feel sort of the similar impulse just from that quote. What I understand is like, steal this company, right? I made the whole company open source. We can have blindness solutions reproduced all over the world in every country. And you can do your FDA approval and whatever that consists of in different countries. I'll do it here in the US. But this is a distributed thing. You steal this company, you start producing this locally, you make money producing it locally for the local blind people around you. And okay, well, I haven't done it yet. I haven't built the software for the company. I haven't built the company yet. I haven't proved the business model works. But that's sort of why most of all of this is open source. So the web page, with the storefront, with the inventory management software, with the patient user login, with the doctor user login, with the researcher user login, for the evaluation viewer, for the prescription editor. It's all in open source web page technology. It communicates to the products, and every product is completely open source. Just to sort of say like, yeah, you could actually, like the whole I'm learning a bunch of DevOps and web page design, which is fun. It's stuff I've never done, but it's all very modern and it's cutting edge, and in Svelte, which is this new sort of. Anyway, I don't want to get into web page design, but I'm having a lot of fun, and it is open source, so the company could potentially be completely reproduced. The shipping interactions, the email is automatically done. What is necessary to run a business? So as I learn how to run a business and I write all of the software and build all of the hardware to do that, I'd like that to be duplicatable and replicable in other countries. In any way, I will get into a little bit about the web page later. And these are a lot of the sort of tools that we use to build that. Free manufacturing, right. So you don't want to have really expensive manufacturing tools. If your product is really specific, like for a neural interface, I imagine that's going to be super complicated to manufacture. And a lot of the products we're using, like the camera, the CMOS sensors on the cameras, billion-dollar fab labs. I'm not going to have that in my garage. So having open standards for how to communicate to the billion-dollar fab lab such that they can produce something for us, that then we can send these same open standards to a different billion-dollar fab lab if we need to switch for any reason. So there's no monopoly over fab lab. So we're using KiCad for all of our PCB design, open source software for everything that we design and do. And those KiCad design files we can send to our PCB manufacturer. And if we need to switch away from that PCB manufacturer, we still have all of our KiCad design files sent to another PCB manufacturer. So trying to stay as open source as possible. We're trying to build a repository of manufacturing tools ourselves. So for we're thinking of an aluminum structure for this pen. So we have a CNC aluminum router that is completely open source that you can build yourself. And we have a 3D printer that is completely open source that you can build yourself. And I think having these tools, all the manufacturing processes themselves open source, again, distributes the manufacturing, allows local jobs and more robust supply chains. So this is a really important slide because it sort of shows the logic of the different products that we're building as a company. So starting with the Pen C, it's composed of various modular components. And how this fits into the ecosystem is that the ecosystem can use these components and recombine them in a hacker ethos to create different products that are not the Pen C. But a pen with a computer in it and a camera in the tip sounds useful. You could do a bunch of stuff with that, right? Beyond just like having a blind person feel text on a piece of paper. So each of these components, power supplies, cameras, FPGAs combined with cameras, those will all be modular, and they are all modular components that are currently available on our website as we build them. We don't have the FPGA up there yet, or the camera, but our power supplies and various other features that we have built are all separate little PCBs that we're selling on our webpage, on our storefront. Those components that are used for the Pen C, what is a light bender? What's the headset? Well, it's basically the components of the Pen C recombined, different 3D printed shell, into, plus a display. So we have to add one display component. What else is there? Well, it's basically just one more display component. And then we have a headset. We take two of the cameras and we take two. So then we follow the same logic to go to, okay, well now what's a neural interface? Well, a neural interface is the headset plus an implant. What else is it beyond a headset? Well, basically, if someone builds the implant and there's an open interface to it, then we can basically take the headset technology and connect it to the implant. It's not a big step. And so these progressions, how these modular parts are separated out into products that we sell, and then how that fits into the ecosystem. And because we're encouraging collaboration by copylefting all of our technology, copy wronging all of that technology. I love how Alex shared that yesterday, different Alex, where I feel very strongly about copylefting technology in a country that has a strong copyleft system. Companies are super afraid of copyleft, and they do use it. I don't know a company that doesn't use Linux because it's super valuable software and it's the strongest software in the world, I think partly because of the copyleft, but also if you're in a country that doesn't respect copyright, doesn't have a legal system that's set up that can enforce copyright for whatever reasons, or if you're just an individual that doesn't care about copyright, who really needs a solution to blindness or whatever you need to use the technology for, copyright and the American legal system is not going to matter in that case. So I think in the case where you're holding large legal entities responsible, it's super valuable. And in the cases where it really matters, where it's out in the world, where people really need it, it doesn't really matter. And I think that's a really important stand to take when you're developing software and when you're choosing a license. And we've done the strongest copyleft licensing on all of our hardware, software, and documentation. I think I get off track on copywriting, but that's the ecosystem, and the arrows go both ways, because when someone modifies the technology and releases it to the public, they are required by law to present it. Thank you. Okay, so this is my last slide. This is the web page in a couple screenshots of our product sales. We've got a LED lens sort of ring. We have a couple power supplies. The point on this slide is that it's international. We have 16, the webpage is completely in 16 different languages. We're looking for international collaboration. We're looking for products to be built and distributed in all countries, in all languages. And all of this software is completely open source. All the web page is completely open source. We're using Libre Translate, which is an open source translation, sequence to sequence language model that we run on our own private servers to do all the live translations. And you're not translating when you look at the page. It's already been translated, so don't worry about all the carbon fumes produced by viewing the page. It's all static HTML. All right, thank you very much.
All right, so now what we're gonna do is take a brief break. I'm gonna ask for you all to come back here at 11:35, and we will from there get on to the next talk. So go, mingle, talk to our presenters, and ask some questions. Also, I wanna highlight we have a bunch of booths in the back that have hardware demos, both immediately in the back of this space as well as around the corner, so go check those out. See you guys at 11:35. Hello. All right, everyone. I'm going to kindly ask that we can start to go back and take our seats so we can get ready for our next presentation. Appreciate you all for calmly going to your seats. We're waiting for. All right, everyone, please start to take your seats. We'll have you come down. Thank you kindly. All right, appreciate it. And also, we want to give a big shout out to Joey Castillo, who's helping us on our live stream. Joey, this hit right here is for you. 5, 4, 3, 2, 1. All right, thank you. So now we're going to have our next talk. So our next talk is Doug Brantner. So Doug has worked as an MRI research engineer for 5 years, designing hardware, software, and sensors for use in the harsh MR environment. He also does electromagnetic, biochemical, ultrasound/acoustic, and thermal computer simulations using highly detailed digital models of the human body. He started out as a stagehand for film, TV, and concerts. Interesting. Occasionally working behind the scenes at medical conferences to now presenting at them, at one point doing physics homework backstage at a cardiology conference, sitting on a road case, using another as a desk while going back and forth to school for math and programming, as we all have done. So with that, I will say thank you for your attention and let Doug do his thing.
All right, thank you for the introduction. My name is Doug Brantner, and I'm going to be talking about open source MRI. I am not associated with any of these projects. I'm here as an interested ambassador. I have no financial interest to disclose related to any of these projects. This presentation was put together entirely by me without any AI. I think machine learning is a very interesting and powerful tool. I think we as technologists have to be very responsible in how we use it and how we talk about it. This is a slide from IBM from 1979. It says a computer can never be held accountable. Therefore, a computer must never make a management decision. I think that goes doubly in medical setting. MRI. Sorry, just need to blow this up. This is not a talk on MRI safety. I was told that important things should be in red. There's a lot of strange physics in MRI. Even tiny little magnets can be very dangerous. There's a lot of RF safety and RF heating, electrical safety, high current, high voltage. Is there any way to make the slides bigger on the computer? Like, just so I can see the whole thing.
Oh, yes, familiar.
There we go. That's perfect. Thank you. Thank you. This is the only piece of medical advice I will give you for this entire talk. If you go for an MRI or X-ray, CT, or any other type of scan, you should always ask for the image on a CD. Ask them for the scan because it'll take some time afterwards, but you should be able to get it the same day. They already gave me an intro, so I won't go through this, but these are some of the sensors that I've worked on. On top, the one on the bottom is actually listed on open source imaging. It's basically an Arduino ESP232 based accelerometer that's wireless. On top is a 3D time of camera. On the bottom is an RF related sensor. These are all related to motion correction or motion detection for respiratory motion, because any motion will mess up an MRI. So this is the signal that we were able to get by placing off-the-shelf 3D camera in an RF enclosed tube with a conductive glass window, and we were able to get a very nice respiratory signal from the subject. This was a motion phantom that I built to test the sensors. This was highly inspired by the COVID respirator projects during, and this is one thing that I really find inspiring about open source is that you can inspire lots of other completely unrelated projects. These are some of the simulation work that I've done. The birdcage coil is shaped like a birdcage. It has very complex geometry, and my boss had some old code to calculate the capacitors for this. And I needed to make like a tiny change in the code to get it to do what I need to do. And I had access to the source code, and I said, hey, can I release this as open source? So open source your boss's old code. I've also done PCB design, helping create test hardware for our RF test equipment using KiCad, proving to your boss and supervisors that open source software can work for you. And this is a pretty complex simulation of biochemistry and stroke that ran on a supercomputer for 40 hours. But this is based on an open source biochemical model of metabolism in the brain based on CellML and OpenCore. So like tons of really cool open source stuff. These slides just leave up for people who want to pause the video later. If you want to talk about going back to school, please feel free to ask me later. I don't have a lot of time, so I did a talk at a hacker conference a couple of years ago, the Hope Conference in New York City, coming up in August if anyone's interested. So if you want a deeper dive into the MRI physics, please check it out. I would encourage more medical professionals to attend hacker conferences. I've been noticing a lot more lawyers coming to hacker conferences and talking about things like privacy, First and Fourth Amendment, right to repair, and stuff like that. Hacker conferences are serious research conferences in the public interest, and I would strongly encourage more medical people to start attending. I am also a fan of plain language in science and medicine. I think my boss thought I was dumb for the first 2 years because I prefer to use simple words, but I think that's the best way to build trust with the public and people. So MRI, that's what we're here to talk about. Thank you. So MRI is magnetic resonance imaging. It takes pictures of the protons and the hydrogen molecules in your body, mostly found in water and fat molecules. There is no radiation in MRI. I think that's very important to note. We were able to get very cool pictures like this through the whole body in 3D using nothing but a big magnet and radio waves. This is actually a series of 2D images, slices that are being scrolled through. So the MRI goes one slice at a time, and it goes one line in the image at a time. That's why MRI is so slow, and that's why MRI motion will mess it up. But I just want to be very clear, there's no radiation and no x-rays in MRI. MRI worldwide access is very bad. 70% of the world's population does not have MRI access at all. There are more MRIs in New York City and probably San Francisco than there are in some countries, and that's really sad. This is because MRI is very expensive. It costs about $1 million per Tesla, which is how the magnets are measured. Typical clinical magnets are 1.3 to 3 Tesla, so that's 1.5 to 3 million just for the machine. MRIs require a lot of infrastructure. You need to basically design and build the building around it. You need access to liquid helium constantly, and you need consistent electrical power. You need trained radiologists and MRI technicians, and you need constant ongoing support and maintenance. So MRI is very expensive. Even in the United States, rural access is very poor, even within a couple hours drive of New York City. Up in the Adirondacks, there are trucks with full-size MRIs in the back of the truck. Some of them are semi-permanently parked at hospitals. Some of them are literally drive back and forth between hospitals during the week. So if you need an MRI and the truck is at the other hospital that day, you're out of luck. So this is what's portable MRI. My question is this the best we can do? Even with a full-size MRI in the back of a truck, 70% of the world population still does not have access. So this is where open source MRI comes in. I'm mostly going to be talking about the one in the middle. That's the opensourceimaging.org scanner. On the right is the MRI for All scanner, which was a hackathon at my previous job, where we built a similar, smaller version in about a week. And on the left is the University of Hong Kong scanner. That's also really interesting. In the recent past, there's been renewed interest in lower field MRI, which means lower magnet strength. Signal to noise ratio, SNR, is proportional to magnet strength. And so only in the recent past, as electronics and post-processing have improved, have we been able to use lower strength, cheaper, smaller magnets. Even there was a 0.55 Tesla magnet. There were only 3 in the world as a research magnet, full-size MRI. We had one at my previous job, and now that's become an actual product MRI. So there's a lot of interest in low field and now mini MRIs. These are two commercial products. In the middle is the Hyperfine. That can be wheeled up to the patient bed for brain MRI. It has this funny little safety zone that pops out to keep people away with metal instruments. And on the right is the Promaxo, which is designed for prostate MRI. These are 0.06 to 0.07 Tesla, and they tend to be more specialized in their use because they have a much smaller field of view. Traditional MRI uses a superconducting electromagnet. It requires liquid helium, which keeps it at 4 Kelvin, so very close to absolute zero. That allows you to have near zero resistance in the coil, and that's how you get such strong magnetic fields, but that's also why it's so expensive. Helium is a very rare, limited, finite resource. It is lighter than air. It literally floats off into the atmosphere and off into outer space, never to be seen again, so please don't do that. And recent political events have also greatly affected the global helium supply. So if we can make an MRI not rely on helium, that would be really good. MRI magnet designs, we call the North Pole, we call that B0. And you can see the traditional design, it's usually pointing down the bore, we call it. There's other parallel plate magnet designs where the B0 field is pointing up and down. The orientation doesn't really matter that much, but it does affect how you design your electronics around it. This is the University of Hong Kong MRI. They use a parallel plate magnet. It's 0.055 Tesla or 55 millitesla. They originally focused on brain MRI. They estimate the mass production cost to be about $20,000 US, and a full half of that is the magnet itself. They designed it so it does not need to be placed in a shielded room. They do active noise cancellation, which is really cool, and it runs on a standard electrical outlet. These are some, on the left is the 55 millitesla magnet, and compared with the 3T diagnostic images, you can see in the second row, this is a patient with a cerebral hemorrhage, and you can see it very clearly on the 55 millitesla magnet. So these are very useful for a diagnostic if you don't have access to a full-size MRI. They've also done whole body imaging, and I put whole body in quotes not because of their scanner. You can see the receiver coil is only covering the patient's abdomen. This is not a limitation of their scanner. This is a limitation of all MRIs, even the full-size ones. MRI has a very small, limited field of view. There's a lot of trade-offs between image quality and speed. Even a full-size MRI can't do a full-body image at once. You have to scan a section, move the patient, and rescan. So this is a limitation of all MRIs, not just theirs. They also do active noise cancellation. They use deep learning for that. So there are some very cool applications for machine learning. So this is a very interesting scanner. And this is the first time I've seen full body images using an open source MRI, because the other ones are too small to fit a patient's torso in. This is the open source OSI squared 1 magnet. This one is probably the most predominant open source scanner. They have a huge support on their website. I highly recommend everybody goes to their website. It's 50 millitesla, 2.15 megahertz. It's about a 30 centimeter bore, which is almost a foot in diameter, so you can fit a head or arms or legs or infants. They quote about 20,000 euros in parts in 2023 dollars. The first image was in 2018. I would highly recommend everybody check out their website. There's over 100 projects on there. Even if you're not into MRI, some subcomponent of this project will probably benefit you in some way, or maybe you can contribute to it. So I'd strongly recommend everybody in the audience, regardless of what your area is, million just scroll through their projects page, because it's awesome. They use a very unique magnet design. It's called a Halbach array. It uses about 3,000 12 millimeter cube magnets that are organized by a computer algorithm. They use the genetic algorithm, which is really cool. Their B0 field, despite being a cylinder shape, the B0 field is pointing up and down. The magnet strength is not really what matters. What matters is the uniformity. Again, talking about field of view, you want to make the largest uniform area of the magnetic field as you can. And then they add, if you see the white, we can't see the pointer. The white ring are these trays of shim magnets to help correct the magnetic field once it's constructed. They also had a really interesting problem when they first built it. the magnetic field was way off and they didn't figure out why. It turns out that the magnets, they have to have a tolerance in the slots to insert the magnet, and all the magnets have these very complex interactions, and they're all torquing each other in weird directions. So they had to go back and redesign the holders to counter rotate the holder so that the magnets would torque themselves into the correct position. So like very weird, interesting problems. And these were CNC'd for precision. This is the MRI for all scanner. We built this at my previous job. It was a hackathon to build a fully working MRI in 1 week. This is basically a smaller version of the MRI open source imaging scanner. We got it almost working in a week with 52 participants, mostly were PhDs or graduate students in MRI. And then they had this, we call it test objects, phantoms. And we did not reveal the interior of the Phantom within the week, but eventually we got it working, and it says together is power. So I think that's a very powerful message for open source. Open source imaging did us one better, and they built a full 3,000 magnet version open source imaging scanner with 4 instructors and 6 participants who were brand new to MRI. And they got their first image in 11 days. So that's very impressive. Their target in Uganda is infant hydrocephalus, which has 180,000 cases every year in Uganda. And so open source imaging has really been pushing as far as like global outreach and getting these scanners to the places they need them. Unfortunately, there's only, I believe, 4 to 6 working ones in the world right now. It's still a very niche project. It definitely needs a lot of support. But the OSI has been doing a lot of work to get these things where they're needed. I'm going to borrow some slides from MRI for All because this is the only one that I've actually had personal interaction with. And they did a really nice job with the exploded view. I'm always a fan of a good exploded view. This one is much smaller. It's more of an experimental research scanner. The bore diameter is 120 millimeters or a little less than 5 inches, so it's big enough to fit a hand. As a climber, that actually would be super useful for people with climbing injuries and hand injuries. So even a small scanner, very useful for research, but also could have some clinical use, especially if you get them anywhere they're needed. This one is a Halbach array of a little under 1,000 magnets. These are 1/2-inch magnets, so 12.7 millimeters. This is a huge supply chain issue because it's very difficult in the US to get 12-millimeter magnets. I know somebody who tried, and it took them a very long time, and they were very expensive. And then the 0.7 millimeter difference actually makes a huge difference in the resulting magnetic field. So you'd have to like resimulate and redesign the magnet between 12 millimeter and 1/2-inch magnets. This one is 0.043 Tesla, and it operates at 1.83 megahertz. So they use numerical optimization to place their magnets. And if you see on the bottom, you can see the green area is the uniform area of the magnetic field. And that's the goal, is to get it as uniform as possible. Then open source imaging created a 3D magnetic field mapping robot. It's basically like a 3D printer with a long arm with a magnetic probe at the end. And then they use that to measure the magnetic field in 3D. They actually did it with full-size clinical scanners. This is like super, do not try this at home. You have to keep it far enough away from the scanner that nothing bad happens. I've seen it happen, not with them, but I've seen it happen and it's terrifying. But they were able to get field maps of full-size MRIs with open source hardware. So once you have your field maps, you measure your magnet, and then you can calculate the shim magnets, which are smaller magnets, to fine-tune the magnetic field. And then the MRI for All scanner, they used active shimming as well, which is a 30-channel array of electromagnetic coils. And that gives you enough degrees of freedom to get theoretically perfect shimming if you have the measurements that you need to calculate the currents needed. And you have the 30-channel current drivers on the bottom right. And they have an interior RF shield, just copper foil on the interior too, to maximize SNR or block out noise. So MRI is looking at the protons in your body. There's trillions of protons in the human body. Proton is the nucleus of a hydrogen atom. Other elements can also be imaged, such as sodium, phosphorus, and oxygen. Those are less common. Most MRIs are tuned for water. And those tend to be more research topics, very interesting. You can do cancer imaging with sodium, which is very interesting. When you place a magnet in a proton in a magnetic field, it will start to precess or wobble and spin. The same way a gyroscope wobbles in the Earth's gravitational field, the protons will align with the magnetic field, and then they'll start to precess at a very specific frequency. This is called the Larmor frequency. I made this animation in processing, which was one of my first open source loves. The Larmor frequency depends on the strength of the magnetic field, so higher magnetic field, higher frequency, and more SNR, and also the gyromagnetic ratio of the particle that you're trying to image. That is unique for every particle. So even you have 1H protons, 2H deuterium hydrogen, and 3H tritium hydrogen. They all have different gyromagnetic ratios, which means that they're all spinning at different frequencies in the same magnetic field, and that's how you get differentiation among particles in MRI. Right now, so we have the protons in the magnet and they're spinning, but they're not doing anything yet. So we need to add an RF coil, a radio frequency coil for transmit and receive, and an amplifier to drive it. This is the coil from the MRI for all scanner, and you can see the shim magnets on the top and the bottom. This is driven by a SDR, or a software-defined radio, and there's a whole bunch of console software that goes into it, which is really complicated. The software behind this is fascinating. I just don't have time to get into it. So what we do is we hit the protons with a very quick RF pulse, and that tips them out of alignment, and they start spinning perpendicular to the magnetic field, and at that point they're emitting radio waves. And then it's a very quick pulse because that can cause heating in the patient. This is the simulation work that I've worked on, is how to avoid what is the safe length for an RF pulse, to avoid causing heating in the patient. And then when you turn off the RF pulse, the protons start to tip back towards the magnetic field, and they're emitting radio waves as they tip back. So you can see the excitation and the relaxation signal, and that's the MRI signal, is the radio waves coming off of the protons. So if you have a tiny little spinning magnet and you put a coil next to it, you will receive a radio wave signal. This is called the FID signal, free induction decay, because it's decaying as the protons tip back towards the magnetic field. And the length of time that it takes to decay back towards the magnetic field is called the T1 constant. That's a unique property of every single molecule. T1 and T2 are the timing constants, that they're unique, just like mass and density. And that's how different molecules are imaged. So there's a whole bunch of hardware in the RF signal chain. Most important here are the preamp, because the MR signal is very weak, so you need to amplify it a whole lot. And you don't want to amplify while you're transmitting, so we have a TR switch in the middle, a transmit receive switch that will block the preamp so you don't burn it out during the transmit pulse. So everything I've shown you so far is enough to do what's called nuclear magnetic resonance. Again, there is no radiation in MRI, so we drop the word nuclear, which only refers because we're imaging the nucleus of the hydrogen atom. We dropped the word nuclear because it was causing unnecessary fear. So again, there's no radiation, no X-rays in MRI. And so far what I've shown you will give us enough to get a chemical signature. This is a super simple NMR magnet, a tabletop with a tiny little bottle of olive oil. And this paper, they showed you can detect adulterated counterfeit olive oil because you can look at the chemical signature. This is only a 1D signal. We don't have enough information to make an image yet. There's also some open source NMR projects on opensourceimaging.org/projects. I think NMR Arduino wins for name, but in order to create an image, we need to know where that signal is coming from. And this is how we do spatial localization of the signal. So in the uniform magnetic field, all of the protons are spinning at the same frequency. But if we apply a gradient or a slope to the magnetic field, then we get slower protons and faster protons all spinning at different frequencies. You can think of this like I used to be a sound guy, so like bass and treble. So all the protons are spinning at different frequencies in a linear fashion. So the frequency depends on the spatial position in one dimension. And then we can also knock them out of phase and use the phase to get the second dimension. And this gets into complex numbers and math. So if you never believed that imaginary numbers were actually useful, it actually comes in handy here. We do this with a set of 3 gradient coils. I don't know if you can see the fingerprint pattern. These are created with more open source software called CoilGen that will it'll create the fingerprint pattern. If you give it a desired magnetic field, it'll give you a wire pattern that will create that magnetic field with a uniform current. So there's 3 gradient coils, X, Y, and Z, and they tip the magnetic field in known directions in each plane. And this is how we get spatial localization of the MRI signal. This was the MRI for all gradients. They 3D printed forms with a fingerprint pattern etched in it, and people placed the wires by hand. It was very stiff wire, very hard work. And they epoxied and put Kapton tape over it. Definitely masks and gloves for this. And also our gradient amplifiers are liquid cooled because they can get warm. The reason you need fast switching gradients is because we're filling in the MRI image one line at a time in this matrix. And again, this is why motion is bad, because we have to fill in the matrix one line at a time. And if you move in between lines, you're going to get motion artifacts. The gradients are switching very fast in the kilohertz range. And this is the audible range. This is where the MRI noise comes from. We're doing one slice of the body at a time and one line per slice at a time. So this is why MRI is slow. And the MRI for all also added a liquid cooling layer to keep the gradient coils cool. There's also the gradient amplifiers, and it's kind of a square wave. This is the RF pulse, and the gradient waveforms are created and sequenced by what's called pulse sequence software. This was typically proprietary for most scanners, so PulseSeq was originally in MATLAB, and it was developed so that you could write one sequence to compile for different proprietary scanners. It's supported by most, if not all, commercial scanners, and now there's a Python fork, and you can use either of them to write pulse sequences for open source MRI as well. This is very important for repeatable research and interoperability. Thank you, Cory Doctorow. And this is what a typical pulse sequence looked like. So you have the RF pulse, the 3 gradient pulses, all timed out perfectly. And then you have the data acquisition window. And then this gets repeated over and over and over again. And that's why you keep hearing like that buzzing sound in the MRIs. This is happening over and over and over again in thousands of times per second. Oh no, is this gonna play? I'm not seeing it here. I was gonna play some music from the MRI, but I don't know if the video is gonna work, so I apologize. So the images are, oh yeah, okay. Is it playing? I can't play it on here. I don't know what's going on. No? Oh, well, sorry. So the images are not images yet. They're actually recorded in what's called frequency space. So you have to do image reconstruction we're recording the frequencies of the signals, because that's how the location is encoded. And if you do an inverse Fourier transform, that's how you get the actual image. So there's tons of image reconstruction software. I don't have time to get into all of that, but again, it's all on the web. There's also this super cool MRI simulator on there where you can just play with all of this on your own computer if you don't have access to the hardware. They have like a bunch of 3D phantoms that you can simulate imaging. You can image them and play with different scan parameters and see what results you get. What's really cool is you can even take an image and then you can reverse the MRI signal out of it, and then you can apply different parameters to that signal, so you can mess around figuring out what sort of sampling you can get away with before you start getting artifacts. So it's like super cool, like stuff you can do on your computer. So open source MRI is great. The problem is there's probably less than 10 of them in the world right now. So access, getting these built is going to be the hard part. So next steps are going to be regulatory certifications in the EU and the FDA. I'm not aware if anybody is working on FDA certification. I believe OSI is working on EU certification. Funding is going to be a huge issue. I would love to work on this stuff. I'm currently looking for work, so if anybody wants to pay me to get this thing open source, FDA certified and open source certified, hit me up. And how do we make more of these? This is like a super complicated project. Like, how do we build this at scale? I don't know. I would love to figure it out though. So I want to say thank you to Lucas Winter from Open Source Imaging, Lior and Kai, Tobias from NYU, Greg and Liana and Radhika from NYU. MRIquestions.com is great. A lot of the images came from there. Thanks, Adam, and all my bosses and coworkers at NYU. And yeah, these are references. The ones that I use most are in bold. Opensourceimaging.org/projects is awesome. MRIquestions.com is awesome. And this is my contact. So thank you.
Okay. All right, so now we're going to give you a double dose of knowledge here. What's it? Well, if you hit him, you could hit him afterwards.
So just a quick point, if you
No.
have all the applications that for the funding, then on the medical, he's also interested.
Okay, appreciate you. So we are going to round out this morning's festivities with a double dose of knowledge between Liz Henry and Olga Priapova. So Liz Henry is the founder and executive director of Grassroots Open Assistive Tech, a highly creative maker, zine writer, hackerspace enthusiast, and disability justice advocate who rides a Will Power Chair and builds community around access. They are a program manager for the Disability Inclusion Fund, Tech, Cross Tech, and advisor to the San Francisco Disability Cultural Center. Olga is an engineer, assistive technology maker, and wheelchair repair enthusiast who serves as an assistive technology program manager at Grassroots Open Assistive Tech. They are currently pursuing a master's in assistive technology studies and human services at CSUN and ATP certification through RESNA, and bring the same curiosity to their work that they do to languages, crafting, LARPing, and puzzles. So with that, I will set up the presentation and ask them to come join us. That's your account leader, and then
I think we can just stick it in here.
Oh, that works good.
How do you do the microphone part? Do we want to just take it off and I'll hold it?
Okay.
Oh. Don't give us feedback. You can just pop that one out and I'll hold it either way.
Hello, it's on. Wow, okay. Hi, I'm Liz Henry, and happy to be here. Love this conference. I love hearing all that stuff. By the way, Corey said, thanks for the shout out. He loves your project. So I'm here from Grassroots Open Assistive Tech. We picked the name because it makes a cool acronym, GOAT. So now we can have like all kinds of GOAT themed things. You know what I didn't ask is how to advance the slides in this computer. Great. So our organization is meant to support free open source software and hardware, anything that allows disabled people to do a repair and reuse for mobility gear and other kinds of assistive tech. We have a lot of different programs, several people on staff, and a big crew of volunteers who are all super amazing. We have a program that focuses on do-it-yourself projects by and for disabled people. We have an archival and preservation program where we take DIY instruction sets, old books from the 70s, really cool stuff that tells you like unhealthy things like how to smoke with, when you're an amputee. So we love all that. We are scanning all that, uploading it to the Internet Archive, and then we chop it up and put it into a big database online. So we have that project going as an archival project. We do maintenance and repair, do-it-yourself workshops. We do research, so we have the RNet program that we mentioned, research and innovation, building, hacking, modifying, really trying to get into right to repair advocacy as well. And basically, in short, we want to get the power to fix and maintain and innovate into disabled people's hands. So to talk a little more about our archiving program, we do a lot with this, the scanning and uploading these old books, but we're also working on new sources and things that people are making up today. And, you know, like I can document the stuff that I do to my own chair and adaptations that I invent out of, you know, string and duct tape. And we are uploading them to also individual DIY items from these books and other sources and from people, from interviews with people, to a site called allyhood.org. This is a program, a project that we're doing as a community partner with University of Washington and other organizations. So we upload the instruction set, link to the source, add really good metadata, and we add like ISO 999 tags, which is like 9999 tags, which is the standard for assistive tech. So this is something we're hoping will then result in getting people building those designs, adding feedback, forking those projects, just, you know, as simple as commenting on it or rating it and saying, I made this and it was good or it sucked. Another thing we want to do with this soon is we want to build, just do a big build for like anything that's an adaptive tool handle. So anything that lets you grip or use like a screwdriver or a hex wrench. We want to make a lot of different plans, and so we'll use everything from Allyhood that tells you how to do that, try them all out and review them, and then we'll have a lot of accessible tools to share. So we run workshops and programs. We want to really provide open access to do hands-on maintenance for people that want to do that, either by themselves or with their support crew, like whoever they bring with them to our workshops. We work with people to figure out what's wrong with their chair, what would they like to modify, what would they like to improve, and how can we kind of get to that result. So we run free community workshops and we give away these free toolkits. It's part of what the nonprofit does. So we pass these out. It's just got some tools, some cable ties, some Velcro, things like that in there that are just commonly useful. And I hear stories all the time from people who have come to our workshops and gotten the kit who say, oh my God, I had that on my wheelchair, and the fact that you had cable ties in there saved me from, you know, just being stuck in the middle of the night on the street. So that's always really great to hear. We run these events at least monthly in the Bay Area. So we also have our research and engineering projects. Ian in the front over there, raising a hand, heads up this ARNet project. Part of the landscape we're dealing with, like, just to outline it for you, yes, you can, if you have access to medical care and insurance of some kind that doesn't screw you over, good luck. But if you have that, maybe you get a wheelchair or a power chair, but you may not have knowledgeable people who know how to get you the equipment you actually need and fit it to your needs and to your body and your capabilities. And a lot more people, even in this resource-rich area of the Bay Area, I know so many people who don't have that access, and so there's a huge market of people buying used chairs or getting donated used chairs and getting them refurbished if possible. Often they just get a donated chair and run it into the ground. That's actually usually what happens. So a lot of what my org wants to do is to really make there be a good ecosystem behind that refurbishing and repair and reuse and maintenance, and really like support that. And part of what we need for that is to be able to program a power chair. So for example, if you have a power chair that has advanced capabilities, like that allow you to say, raise the chair up, it might have a setting, it does in fact have a setting that means if you're raised up like this, you can't move yourself. You have to, you know, you have to go through like a bunch of rigmarole. Or if you're tilted slightly, you can only go 1 mile an hour. And nobody wants that. And it's not actually something that keeps anyone safe, in my opinion. But a lot of people need to also reprogram their chair or a refurbished chair that they get their hands on because their capabilities might change. So they start out with a chair that they can drive, and then they need to program it differently. They don't have access to the programming. The technology is proprietary. There's all kinds of background there. But there are people who have written open source libraries to use the protocols. Like a common protocol is built on CAN bus, which is the same thing used in cars. And then a library called ARNet, which is closed source. but now we have an open RNet library available on GitHub for people to use. And we've used it and built like little devices, and we're working on this project to dump all the information out and be able to figure out how to configure and how to do diagnostics on the older power chairs that we get our hands on. So yeah, speaking a little more to that refurbishing really takes a whole ecosystem of, you need a lot of old chairs. Where do you keep them? So we get donations of giant amounts of power chairs and then have to spread them out around the Bay Area because like warehouse space is quite expensive and no one has space. So there's lots of little organizations in all the different cities and counties of the Bay Area that have a stock of old wheelchairs. Sometimes they're nonprofits, sometimes they're part of a independent living center or other agency, like the Veterans Administration has them and is always trying to offload them onto us, which we appreciate actually. But you really need like more warehouse space and more material space than you think you will. You can't just have like 3 chairs. You have to have a giant graveyard, a junkyard, basically. You need like wheelchair pick and pull. And you need a workshop and tools. And ideally, that workshop and tools, in our mind, would be open and available. It's not just something where you take your wheelchair and you hand it over to somebody, and then what? I don't know. You roll away and you know crawl away. And no, you need a loaner chair. So you need like loaner material that actually fits your circumstance. Otherwise, you're going to be trapped in bed. Could be months, could be a year. You know, it could be that you never get a chair that ever fits your body again. And there's not a lot of accountability once people take your chair to go try and fix it. So we really want to change that landscape at the grassroots level. And the other problem that I think Olga can speak to really well is that there isn't a good pipeline for learning these skills for anybody, not just for disabled people, but for anyone. So when a local wheelchair shop, if you're lucky enough to have that, which most cities don't have that, our region has had most of them kind of go out of business. We have a few left standing or sitting. The problem is who do they hire? Like, how do you find a wheelchair technician? It's not something they teach in city college, you know, in community college. So they hire auto technicians, bike shop technicians, and just kind of teach them on the job. So the wheelchair repair and maintenance qualifications and learning pipelines actually come mostly through the companies, and the big companies that do repair. There's 2 of them, New Motion and National Seating and Mobility, I guess. Maybe Invacare also. Are they the same thing? I don't even know. So there's sort of corporate, like people who will train you to be a technician, but only within their system and within their silo, and they don't really share that information much outward. So that's the landscape we're looking in. We're looking to change. We're holding events. We're trying to have our free workshop and have accessible events and accessible tools. You also kind of need the freedom to tinker and mess up. So as open source hackers, right? We know, like in a hackerspace, you can screw around, you can mess around, you can mess things up. If you've got one wheelchair and your whole life depends on it, you can't mess it up. So you need your chair, your backup chair, and a whole extra chair to hack, or somewhere you can go that means that you can learn. Like you need demonstration chairs to take apart and to practice maintenance on so that you can do it on your own. So we're really trying to support that. And to that, we've actually opened, just this month, we've opened a makerspace in downtown Oakland that's a makerspace for, like a hackerspace for assistive technology. Right now, we're heavily wheelchair focused. We got a huge donation of wheelchair parts and used wheelchairs and tools, and we got cheap rent. So this allowed us to open this space, and it's super exciting. We're gonna host our workshops there, as well as in other organizations. And we hope to have more news about that in the future. Part of what this can really do in holding our workshops, like a dynamic I see is that people come in, something is wrong with their chair and they want to talk about it. And it's kind of like a traumatic thing. Like when I talk about times that my chair broke and I was like stranded in an airport, I just feel my heart pounding and I feel like I'm gonna cry and I want to tell the story and I'm just like, wow, I'm really kind of trauma dumping. But that's kind of where I go with it. And we want to take the experience of like having the relationship with your technology that is really integrated with your body. Like we want to make that more community joy focused. It sounds like a cliche, but we want to just make the healing the equipment be part of healing your whole relationship and your integration with your technology. And if we have a more, a healthy is the wrong word. If we have a more holistic approach to how we maintain our stuff, I just think it's more, it's better for us. It's better for like the long-term life of our gear, and just better for the world in general. So I'm going to hand it over to Olga to talk about a specific implementation we did. Do you want to give the background? Should I introduce it? You're going to introduce it. Okay, I'm going to just hand you the microphone.
Thanks, Liz. All right, so the second part of this talk, and I'll try to go quickly, is about the service delivery and access in a very rural area. So let's meet Andre. Andre has SMA, and it's gradually reduced his ability to drive his chair. He lives in East Europe, very far away from even core cities. He got a used power chair, but then quickly learned he can't drive it. And he's very tech savvy, resourceful. He can research a lot of things online. He tried everything, and then he realized like he can't figure out a way around it or to get this wheelchair to serve his needs. So he went on Reddit, and that's when we found about his story and this challenge. So our go question was immediately like, what would it take to get control back of this chair? And we didn't know much. We were new to this landscape, so we paired up with other organizations. We hopped onto Zoom meetings with Andre with a little bit of translation back and forth in different languages, and all these organizations trying to contribute information and knowledge. We had an occupational therapist to review how Andre is sitting, to give some suggestions about alternative driving joysticks that might work. And then we took on this whole challenge of like, what do we do next? So we quickly realized that it wouldn't be the kind of solution where you can just ship something and be done with it, or even donate some money to the person because they're in a rural area, they don't have access to the tools, to the knowledge, to this information. So for several months, we were putting together a plan. We were raising up costs for travel. I flew over to Moldova to reach Andre, and in the 100 pounds of luggage allowance, I tried to pack up as many things as I could and prepare as much as I could for that plan. So that's kind of like, if you had those kind of constraints, what would you pack and prepare for, right? Like you can't just go there and be like, oh yeah, I forgot that one thing, So we try to prepare as much as we could. And being an anxious engineer, you kind of plan for a plan B and a plan C and a plan D and everything in between. We packed 3 different joysticks, a mini, a micro, and a chin control joystick, different mounting hardware, extra tools, extra foam, backup parts, different service manuals, all of that stuff. But most importantly for me, being new to the space, is practicing on other chairs that are similar to Andre's ahead of time to be able to set one thing, set the other thing, connect it all together, take it back apart, readjust it, things like that. So big thanks to all organizations who helped us along the way to get there. And then there was that magic moment where Andre drove for the first time. The original solution, the small joystick installed on the tray, did not work, and then we switched it to the chin joystick, and there's a little GIF video on the screen of Andre like being able to pivot his chair, being able to drive it back and forth and turn around. And that was like this moment we were working so hard for. That's kind of the moment where I could finally breathe, because I was just holding my breath. They're like, I hope at least one of our solutions is going to work, because we were so invested in this. And the next 3 days were the most fascinating to me, because this is where we were able to figure out things in real life, and this is what we were preparing for. I'm so glad we had those 3 days, because some things did not work as expected. Our original mounting solutions were like, oh, actually, whenever Andre gets transferred into the chair, he sits a little differently next time. If we keep that tray in front of him, like now his mom needs to a set of hex ranges and like try to every day adjust where its position. So just no go. So we just took it out. We rebuilt like where the joystick is attaching to the chair. We got to take it outside on the actual streets of the village. There's a little gift there with Andre's dog running around, being super excited that Andre's finally able to take him for a walk. And after that, we left, but we stayed in contact. And what I loved most about it is because during that process, during those 3 days, we were able to work together to build a solution that worked for Andre, to include his mom in training to how it works. It felt like it's his device now. So he put on a bunch of stickers on it, some of them that Liz sent. So there's like the wheelchair on fire and different open source Mozilla stickers and other variety of open source things. Andre's mom figured out how to put a little cart for the dog so that Andre can have him ride in the back when he gets tired. And they build a really comfortable solution to the left armrest because Andre sits while leaning to the left, so it had to be able to support his weight comfortably. And that's what I love to see, like knowing that this person can continue to evolve their chair to their needs means that it's theirs now. Like we have accomplished what we really wanted to, not like we dropped something and then left and now it doesn't work, but it kept growing. So that's kind of the biggest takeaway I want to leave you with is kind of what stays after you leave. And hopefully if you prepared for it and had all your backup plans work out, then you left not only the parts and the tools and the documentation, but also the confidence and all of the options that this person can now leverage. And some pictures of Andre during different weather conditions, riding outside with some of the smaller additional things that they've made, like there's a more comfortable wrap next to his left arm and a little ribbon connecting the chin joystick so it doesn't fly away on the big bumps of some other roads. Yeah, so thank you so much.
Oh, yeah, just to say, you can come visit us. Here's the URL. I realized I hadn't shared that in the slides anywhere. So it's just openassistivetech.org. And like I said, we're in downtown Oakland. So if you're around next week, we'll be open Monday through Friday. And you can email us and come on by or just come and chat with me. Oh, what time? 10 to 4. Weekdays, 10 to 4. But yeah, there's a lot more information you have to get from the website to find us because it's a very mysterious process. I think the punchline of that story about Andre is also that he was so great to work with in this whole collaborative process. And he's just so like smart and awesome that we ended up hiring him for the organization. So now he's our like IT guy. And we keep doing that. Like in our workshops, you know, someone shows up for their wheelchair to get fixed and they turn out to be so handy and so interested and so like kind of DIY-ish that we're like, hey, come work for us actually. So that's been really a joy and part of the point of the organization.
Thank you.
All right, and with that, that will conclude this morning's sessions. So now we're gonna have everybody's favorite part, lunch. I'll ask you kindly to come back at 1:50. And so while you have the time, eat, connect, network, and check out the tables. We'll see you guys in a few.
MC duties, and we're going to start with Aaron McKiernan. Is that right? Okay. Is a professor at the Department of Physics, Biomedical Physics program at the National Autonomous University of Mexico in Mexico City. She has a bachelor's in psychology and both a master's and PhD in psychological sciences, all from the University of Arizona. Erin is also an open source advocate and practitioner, and is the director of programs and strategies for the Open Research Community Accelerator, a nonprofit working to make science more engaging, accessible, and actionable. Please give it up. Let me get your slides loaded.
Yeah, we get that. Hey, everyone. Thanks for sticking around. I know the after lunch spot is always a bit tough, so I will do my best to keep you all awake. And we're going to change gears a little bit now. Instead of talking about the generation of new open hardware or healthware, I'm going to talk about the use of open hardware in an educational setting, specifically to train the next generation of biomedical researchers and medical professionals. So that's the idea for today. I think we can go to full screen. Awesome. Thank you so much. Yeah. Okay. So yeah, as you heard in the intro, and I think we've switched mics over here, so I'll come here, is I am, in addition to working in open science advocacy, I'm also a professor based in Mexico City. I work primarily with undergraduate students in our biomedical physics program. And over the last 10 to 15 years, these are some of the challenges that we've seen in terms of providing biomedical education to our undergraduate students. First of all, we're working in a public university environment, and we have very high enrollment. To give you an idea, UNAM has over, I think, 360,000 students in its entire system. So that strains our capacity quite a bit. The other thing is the region itself has limited financial resources, right? So if we talk about providing quality educational experiences for our students, it's not always possible to buy the newest equipment or even a lot of equipment that would cater to the size of our student population. We have a scarcity of materials, we have a scarcity of adequate infrastructure, and so that makes it difficult to provide those hands-on learning experiences that we really want to provide them. In particular for biomedical students, we want them to learn the newest the newest and also the classic techniques that we have in electrophysiology, like recording their hearts with electrocardiography or recording their muscles with electromyography. That's something you really have to do hands-on. And so when we started this work, we had two kind of fundamental questions. What are the open science strategies and technologies that might help address these challenges that we have in the region? And then also specifically, how can open hardware and open software help us build greater capacity in terms of the educational experiences that we're able to provide? So we started this work in 2017 with the idea that open hardware would, not sure I'm getting feedback here, there we go. Open hardware would allow us to build that capacity. We were looking for a few different things. First of all, low cost, right? When we began this work, it was with a total budget of $10,000 US, and so we really needed to provide kind of the best bang for our buck and make sure that we were investing that money wisely. We also wanted to have the freedom, as open hardware gives us, to modify designs, make our own copies, do all those things, and have a transparency behind it as well. We don't want the students just to be working with a black box, but we want them to understand how that technology works and how it's allowing them to record biopotentials in a human patient, right? The other thing we wanted was portability. So again, with the kind of inadequate infrastructure we sometimes have, we don't always have the right number of classrooms or laboratories to be able to work in. So it's important that the equipment we have can be taken to any classroom in any moment. So you'll see a few examples here of some of the technologies we started to use from Backyard Brains, from Upside Down Labs. These are, again, open hardware that allow you to record electrical signals that are coming from the body that get used a lot in biomedical research and clinical applications. So one of these, Backyard Brains. How many are familiar with Backyard Brains? Yes, okay. I'm a huge fan. This company was founded, I think it was 2011, 2012, around there, with the idea, this motto of neuroscience for everyone, right? So they really wanted to build technology that would make science more accessible, and they have kind of a special focus on K through 12 outreach and education. So we started using a lot of these devices, and you'll see a couple examples here. On this side, you'll see an example of the device they have for recording electrocardiograms. So again, this is recording the electrical activity of your heart, a pretty common diagnostic tool in biomedical research and the clinics. And so on the other side, you'll see an example of a device that's for recording muscle activity, so electromyography. The advantage of these technologies is instead of the thousands of dollars that it costs for one of the clinical grade devices, these are $200 a piece. So we can buy quite a few of these. They're highly portable. They fit in the palm of my hand and they can go to any classroom, any lab. I can record on the street if I want to. They connect to the students' smartphones. So again, you don't need any additional kind of infrastructure. You just plug and play. And they're open software, so the software we're using to record and look at these signals, totally open. The hardware is open, and again, hopefully we can in the future make our own low-cost version. So ideal for an educational setting when you're trying to get the students that hand-on experience, learning experience. The other one we recently discovered is called Upside Down Labs, and I think they even based some of their designs on the original Backyard Brains designs. But these are even lower cost. And again, all their designs are available online. So here's an example of a few of those sensors that are used to record biopotentials. We see examples here of one that's used to record EMGs or electromyography. This is a wearable EMG sensor, so you can stick it on your arm and kind of walk around with it. There's another example here that's for recording electrocardiograms. And then there's one that does all kinds of different things. And all you need to do is take this little sensor. It's about $10 to $14 per sensor, hook it up to an Arduino, and you have a portable EMG or EKG system for your students to play around with. So fantastic technology. We're now using these a bit more, and I'll come back to that later when we talk about future work. So to show you a few examples of what we're doing, these are my students in their core human physiology course. So they have a cardiovascular physiology module where they learn about the electric activity of the heart. And then with these devices, they get a chance to record their own hearts. So they're sitting in class, they're recording their own hearts, their friends' own hearts, and then we do a little experiment where they disconnect, they run up and down the stairs outside the classroom, and then they come back and record their hearts again. And they see the effect of exercise on their heart activity. So really nice way for them to strengthen the knowledge that the theoretical knowledge, right, that they're learning in this module, and then explore the effects of exercise, but hands-on interactive learning. Here's another example. This is an electrooculogram. So this is actually recording the movement of the dipole of the eye. And so when you look left, there's a deflection in a certain direction. And then when you look right, there's a deflection in the opposite direction. And so you can see the student here recording. This was in our Physics of the Human Body course. And this allows them to reinforce the theoretical concepts they're seeing on physiology of the eye and play around with those signals. Here's another example, and these are my favorite devices. The EMG devices, I think, are the most versatile, so you can do all kinds of different experiments. So these are students, again, in the human physiology course. They've just learned about the muscular system, and now they're recording their own muscles. They do recordings of big muscles like biceps or little muscles like ones in the hand that control finger movements. And then they do a series of experiments which they ideally design on their own. So we use things that are in the classroom. They pick up their backpacks with books in them and they lift them and they learn about muscle fatigue. One student here, I think, is chewing gum and recording the signal when they chew gum. We even had some students bring in food that was of different textures and then looked at how the signal changed when they chewed foods of different texture, different resistance. So again, really great. And not only are they strengthening the theoretical concepts from the class itself, they're also starting to learn in the early stages of their education about research methods, right? How do I ask a question? How do I design an experiment? How do I interpret the results? So just building those general skills early on in their career. Here's another example where they're starting to integrate knowledge. So here they're recording the EMG, the muscle activity for accessory respiratory muscles, muscles that activate when I do a forced exhalation. and recording spirometry at the same time, so volume of the air going in and out of their lungs. And this is great because usually the way they learn about physiology, it's very modular. And here they're getting a chance to integrate knowledge from two different systems and see, okay, here's the mechanics of respiration, and that's how that relates to the volume of air going in and out of my lungs. So what did we do with this? When we created all these materials, something that was important to us was to share those back out. We don't want this project to just affect what happens at the local level in our university, but we want other people to be able to reuse it. So we created a GitHub repository for sharing all these educational materials. If you scan the QR code there, you can explore that repository. And it's organized by technique. So we have EMG recordings, EKG or ECG recordings, EOG, which is the oculogram, and a few data science tutorials to allow them to analyze those data. And that's the other thing we think was important about this repository was we're not just providing written documentation for how to carry out these educational activities, we're providing a whole suite of open science materials. So we have the original recordings, the data are available in the repository. We have analysis code that we've developed in Python that's in the form of Jupyter notebooks, so they can interact with that code, go through and analyze the data, replace the files with their own recordings and analyze that. And then we have the written protocols that allow teachers to reproduce these activities. So we have this suite of materials, and we do think that each one kind of feeds into the other, right? So each time that I rerun this activity, I create more data. Each time I create more data, I can improve my code to analyze those data. Each time I improve the code and improve my Jupyter notebooks, those themselves turn into educational materials. So there's a whole kind of open science ecosystem that's supporting this educational experience. And so that was really important for us to do. If you'd like to read more, we did publish a paper that was all about how we were using these open science approaches to build educational capacity. And again, particularly thinking about the Latin American context where we're working with limited resources. How does open hardware or all these open science approaches together help us build that capacity? So that was the first phase of the project. And the idea from there was, could we take this and now expand it and reproduce it and get other faculty to start using these technologies in the classroom? Up until this point, it had just been me kind of doing this with my group. And we wanted to see if we could create a training program. So we got lucky in terms of the timing here. The Chan Zuckerberg Initiative, this is a philanthropy that is interested in biomedical sciences. At the time, they were opening up a new call that was for funding projects in Latin America with a biomedical focus. So we applied for this grant. We got 2 years of funding that'll run out the end of this year. And we started to create that training program. Again, can we reproduce what we learned in the early stages of this program, get people excited about using open hardware in the classroom, and create something that could reach more students and more professors? And so the goals of the project were a fewfold. So in general, what we wanted to do was promote the use of open hardware, promote the idea that open hardware helps me build educational capacity, specifically in resource-limited environments, and helps me provide those hands-on learning experiences for students that I wouldn't otherwise have the opportunity to provide. We wanted to reduce these barriers for professors and get different disciplines involved, right? Science increasingly is an interdisciplinary endeavor. We don't just want folks kind of focusing on their one discipline. So we wanted to get folks from physics, from biomedical physics, from biology, from even applied math involved in this program and integrate these activities into their coursework. Collecting and sharing electrophysiological data, for us, that was another way to lower barriers. So if we think again about the repository and that ecosystem of open materials you have, let's say you're not able to actually purchase the equipment, you can still grab those data and start playing around with those data. And that's another way for your students to get a hands-on learning experience, even if they don't have the equipment available right away. And that was, again, one of the motivations too behind developing some of these open software tools that go along with the recordings. It was also another way for us to strengthen sort of the programming element of our degree program, to say, hey, you're learning about programming, but wouldn't it be great and kind of more motivating if you were able to analyze data that comes from your own heart or from your own muscles or from your friend's muscles? That's going to generate more enthusiasm in the students than just grabbing some data from a database online. So we started by piloting these experiments, these activities, this training at my own university in Mexico City. And then the idea was to branch out and go to other universities in the region. And in a moment, I'll talk about how we did that. So what does the program actually do? Something for us that was very important was to provide multiple ways for people to participate and not kind of add to the extra burden. A lot of professors have a significant teaching load. We don't want to add to that. We want to make it something that's easy to participate in. So we sort of have this scale. Some folks just did a one-time workshop, and that's okay. If they never come back, at least they heard a little bit about open hardware. They've been introduced to the idea. They can think about it. A lot of folks participated kind of at this third level, which was we'll come into the classroom and we'll pilot these activities with your groups. And the reason that's a great strategy, I think, is because it not only kind of simultaneously shows the professor how to do these activities, but it also shows them in real time the benefit for their students. Their students get excited, they get excited. There are higher levels of participation, which we did get some folks to go up to these higher levels, including integrating these activities into their regular curriculum, and then even a sort of a train the trainers model where faculty that we had trained in previous workshops then went on and trained their other colleagues to do this. And that happened organically, and that was really great to see, something we'd like to do more of. So to show you a few examples of this, here's an example from classes in physics and biomedical physics. So the ones here on the left are students from a second semester. They're just starting out, and they're in a course that's supposed to show them about measurement and experimental processes in physics. And so really, really crucial that they have the hands-on experience, grab equipment, let's record your muscles, let's get some data, and then let's figure out how we're going to analyze those data. So this is an example where they're recording their hearts and kind of looking at that signal. On the right, we have an example from a class we have that's called Physics for Biologists. And in here, we actually have them using another Backyard Brains device called the Roach Scope. This is an open hardware microscope. You put your cell phone on top, turn the light on, and all of a sudden you have a mini and very portable microscope. So we were able to look at some brain slices in that class. They were able to look at leaves and the little veins on the leaves, and even grab some water samples from a fountain in front of our faculty and looked at all the microorganisms that were living in our fountain. So again, hands-on learning. Here's an example that I really loved because, again, one of the motivations was to reach out to other disciplines. These are students in a relatively new degree program in applied mathematics. And as you might imagine, they don't necessarily get a lot of chance to do experiments in their classes. A lot of their classes are theoretical. At the most, they might have a chance to do some real-time coding, but they don't get a chance to do experiments like this. And so we brought the equipment. They recorded their hearts, they recorded their muscles, and then they later analyzed their own data, which I think was exciting and motivating for them, and another way for us to bridge that disciplinary kind of gap that we have sometimes. And here, I'm going to talk a little bit about our big success story, which was our work with the School of Medicine. So the School of Medicine at UNAM is one of the largest medical schools in Latin America, if not the largest. This is undergraduate level education, I should mention, not graduate level. And we went in and ran workshops, first of all, for their professors and said, here's the open hardware. Here's what we're thinking you can do with this. Here's the advantage. You guys have only one or few devices that are clinical grade. Your students have to stand in line for an hour, record 10 seconds, and then leave. That's not an interactive learning experience for them. So we brought this in, and these are actually the professors that are recording their own hearts and their own muscles and getting excited and seeing the potential. Once we did this, we then had a subset of those professors that invited us back into their own classrooms, and we ran activities with over 300 students in the medical school. So this is an example of that. You can see folks were doing push-ups, folks were getting on top of the table, folks were chewing gum or chewing food, and all this time they're learning about these techniques and applying that theoretical knowledge to a practical situation. So we ran about 50 hours of practicals, and then we surveyed both the students and interviewed the professors to see what was the impact of this program. Was it successful in doing what we wanted it to do? So here are some survey results, and I think they're really positive. So the first question was, I understand the techniques that I'm learning in these activities. It was accessible information we were giving them, 94%. This practical helped me understand the concepts we're seeing in class. That's one of the goals we have, right? Is to translate that theoretical knowledge into practical knowledge, 95%. And then this interesting one, especially for us open science advocates out there, was I now have a better understanding of open science materials, technologies, and their possible uses. And that was 90% as well. So for those of you who run surveys, these are pretty good numbers, and we were pretty happy about this. We also did some kind of qualitative analysis. So we had open-ended questions and asked them, what did you like most about this activity? It's in Spanish, but basically they're verbs that say, it was easy, we could see, right? Poder ver is we could see. We could see the actual things we'd been talking about in class in real time, right? And so that was the thing for them, I think, that was most exciting. When we interviewed the professors, they had similar positive feedback. And these were kind of some of the themes that came out. So when they were using open hardware, and this is the first time that most of them had used any type of open hardware, they said that it increased active learning and student agency. They saw in their students kind of a better integration of the theoretical knowledge with the practical experience. They had this idea of democratization of educational resources, right? Again, they'd been working with very costly equipment that had been donated, that they didn't have a lot to work with. And so they saw the potential to kind of democratize these experiences. And then an increased awareness of open technologies. But it's not an increased awareness through just pure advocacy. It's actually showing them in real time the promise of these technologies. What can the technology do for them? What problem does it solve in the classroom? And how does it help my students? And that's really the thing that gets them bought into the idea that open hardware is something they should be using. So again, if you'd like to read more about this project, we do have a preprint online. This is about the specific case study that we did with the medical school. And now we're trying to reproduce these results with other departments, with other faculties within our own university, and then with other universities in Latin America. We've also put online some more in-depth educational resources. So this is a book that we've put, an ebook that we put online through CurveNote, and this has all of the experimental and computational practicals that we developed with respect to electromyography, so muscle recordings, right? And again, all of this is openly licensed. All of the code is developed with Python and Jupyter, and all of the experimental practicals are using open hardware. How are we expanding? So again, the easiest thing to do at first was to pilot at my own university. I knew that environment. I knew the folks that I could reach out to. So we started at UNAM. We reached out then to a university in Sonora in the north of the country. And now we're expanding to other regions in Latin America. We hired a coordinator in Argentina. And so she is reaching out to universities there. So some of these we've already done. So in Colombia, for example, we've done both in-person and online activities. In these other countries you see on the map, we have workshops and other activities lined up throughout the year, and we will be going to those universities to do site visits. The other thing we're doing is donating equipment. So we realize that there's a certain amount of investment, even if it's low-cost open hardware, there's a certain amount of investment involved here, and people really need the equipment in their hand to start doing these activities with their students. So the other thing we're doing is when we go to these site visits, we take packages of equipment and we leave those with the universities. And all we ask is that they send us great photos of their students doing exciting things, and they kind of report back to us what they've been doing with the equipment. And that sort of brings us to our future work. So again, one of the potential limiting factors here is, do you have the open hardware available to be able to do these things? And even though the Backyard Brains devices are relatively cheap with respect to clinical grade equipment, it's still an investment, right? Especially if I have hundreds of students buying enough equipment at $200 a pop, is not a small investment. So what we started thinking about was, what's the long-term plan here? How can we help universities acquire this open hardware? And that's where I'm going to return to this company I talked about earlier, which is Upside Down Labs. So as you know, the Backyard Brains devices, if I want to buy a fully functional, device for EMG recording, that's about $190, $200. With Upside Down Labs, their EMG chip is $10. Now, it's not fully assembled. I still need to hook it up to an Arduino, but that's relatively easy. And then, another $10 for my Arduino, and I have a $20 EMG device that's portable and I can take anywhere I want. They're not as user-friendly, I will say, as the Backyard Brains ones. So one of the things we've been doing is, could we build 3D printed housing that allows you to slot in the chip for EMG, slot in the Arduino, hook up the cables, and then give folks that fully assembled device for $30, let's say, right? And so now when we're going to the universities, these are the packages of equipment that we're donating. Because of course, with that cost, we can build more, we can buy more, we can build more, and we can donate more. The other thing we're working on is other instrumentation projects. So we don't want to just stick with the electrophysiology. We want to be able to do other things that are relevant to biomedical sciences. One of those is imaging, biomicroscopy. And so I don't know, people must be familiar with Open Flexure. Yes, okay. So this is an open hardware design for a little microscope. And again, these are open hardware, open designs, and fairly portable as well. So we're starting to fabricate some of those. We're starting to look at other options. For example, we've funded recently a professor who's going to build spectroscopy open hardware. So excited about the kind of next phase of this project being, not only do we have all the training materials online and the resources for people to do these activities, but we're actually putting open hardware in their hands and encouraging them to start using it, right? And so I want to say a big thanks to the ORCA team and the ABRELA team, which is the name of our project, Advancing Biomedical Research and Education in Latin America. Specifically to Nara, who's our coordinator in Argentina, who's done a lot of this work. She was the one who came up with this design for the 3D printed housing and has been amazing and is now helping us expand the program. But really all the team who are amazing partners in this work. And if you're in the region or folks in the region, please reach out, because again, we're looking to reach as many schools as possible. The other thing we're hoping to do in the future is go to minority serving institutions in the US. We think that's also a place where open hardware could have huge impact in education. So we're working with some partners at HBCUs and hopefully starting another version 2.0 of this at MSIs in the US. So I think actually I will close early, and I know we don't have questions, but if you'd like to contact me, easiest way is Erin@orcaopen.org, and happy to talk with all of you. So thanks so much for your time.
Very cool. Oh. Testing. Test that again. All right, there we go. Yeah, that's awesome. Okay, next we have Alex Barton and Jack Keenan. Would y'all give me just a sec? I'm going to get your slides up and then bring you up here. Yeah, I know. All right, thank you. And so welcome to Alex and Jack. Alex is a founder of DMDM. He has a bachelor's in data analysis and is a certified quality engineer through ASQ. Alex has worked in the medical device field for 15 years, specializing in practical quality management. Jack is an industrial sewing and operations expert with DMDM and leads the sewing training program. He has diverse experience in manufacturing and fabrication and a long history of frontline activism. Welcome.
Hey, good afternoon. Great introduction there, so I don't think we need one. I'm gonna pull up these notes real quick. No. Let's see. Do you happen to know how to get the presenter notes up?
Let's check a different tab.
Guess while we're getting it up there, been a hell of a lot of good speakers today, and this is such a cool opportunity to be in a room with such talented people. So very excited to be here. Okay, so I guess we got a really good introduction just then, so I'll pass it over to Jack to explain a little bit what DMDM is.
Yeah, welcome everybody. DMDM is a small-scale manufacturing collective producing tourniquets in our FDA-registered facility in Tucson, Arizona. We produce the GLIA open source design tourniquet.
Okay, so a little bit of background. I founded DMDM with a few other people in 2022. This was based off of Mutual Aid Disaster Relief, which is a disaster organization that I was a part of for a long time. I was inspired by GLIA's work in Gaza and the work being done during the pandemic, and kind of this groundswell of mutual aid where we realized that we need to really start taking some of the care into our own hands. And so we kicked it off then. If you're not familiar with GLIA, make sure to stick around tomorrow. Jen is going to be presenting a talk at 10:30. GLIA is a nonprofit founded by Dr. Lubani, who design open source medical devices. They do very good quality work, and I would highly recommend checking them out. Oh, and kind of a prelude to us starting GLIA or starting DMDM was we wanted to make sure that we were able to build these correctly. And so we started a field trial through a few other organizations in 2023 where we tested 120 tourniquets in field conditions. We got the data back from that, found that it was safe and effective, and so decided to start seeking funding and started DMDM in earnest.
So after those successful field trials, we crowdfunded our initial funds for our FDA registration in 2024. So we raised about $10,000 through GiveButter, through our local network. And in fall of 2024, we started production in earnest. We bought an industrial sewing machine and started training sewers, including myself. I came on initially to DMDM through the sewing program. We moved to a larger facility where we could kind of expand our manufacturing capabilities. And since then, we've made 2,000 tourniquets. We've shifted to a 5-member collective structure that sort of steers the ship. We have 5 paid sewers. We've trained over 100 volunteers, gotten a couple of grants, and have run 4 successful crowdfunding campaigns, specifically to send tourniquets to distant destinations and destinations here at home: Haiti, Lebanon, Minneapolis, Los Angeles, and mutual aid medics and street medics around the country. So a little bit about how DMDM is organized. We do all of our manufacturing on a work party structure. We're a volunteer-run organization. So the way we get the work done is we publicize our weekly events. We have one every Wednesday. You can see that's our manufacturing space that we share with a few other aligned groups in Tucson, Arizona. And we have a weekly routine manufacturing workday on Wednesdays, and we'll publicize bigger like emergency pushes. We had the opportunity to send tourniquets to Southern Lebanon through Distribute Aid earlier this year, and we were able to pull a lot of volunteers to get a lot of work done. A little bit more about our structure. We have those 5 central members in DMDM, sort of making admin decisions and like guiding where the organization will go. Beyond that, and including those people, we have specialists who are experts in the manufacturing of the tourniquets. So they know the ins and the outs. They can train our volunteers on this sort of like outer ring of our organization. So we have a lot of people come through. We train them in the steps as we come to them, depending on what work is available. Specialists document that training, and they do inspections on the work to maintain a high quality of work. We've really enjoyed a consistent volunteer presence with DMDM. It's made running the organization like a lot easier. We have very dedicated people, and we often go in waves of seeing the same 5 or 6 people for months at a time. It's like a really nice social environment. I think this model introduces some interesting questions about scaling, just in that we are a fairly small scale operation, but we are stratifying the work of the volunteers somewhat already. We contract sewing to experts that are trained by our sewing program. We started with friends and local people that sew in the Tucson area and have moved outward to people that we didn't know at the start of the sewing program. We have a few tasks that we don't do at volunteer days. One of the materials we use is Omni tape, if anyone's familiar. It's Velcro that sticks to itself, and cutting this is a very chaotic operation that we don't do with volunteers anymore. We've had a lot of work days of 6 people standing around our automatic cutting machine trying to grab Velcro before it jumps to itself. So we are stratifying the work somewhat. And I think that this interplay of volunteer labor going to specialized labor to sew, back to volunteer labor, back to sewers, and contracting some of that work are the beginnings of scaling to a more complex device, that maybe some of it needs to be contracted out from the beginning, but then volunteer labor can be really helpful in simple assembly and slightly more technical tasks. Our goal with this structure is to have a really low floor for involvement. So even people who don't necessarily come to us with a background in like handcrafts or manufacturing can get the training they need to be really helpful really quickly.
Yeah, and just to emphasize, none of the members in DMDM are paid for any of this work. We all have day jobs on top of this, but we fit it in and it brings us a lot of joy. So we're going to talk about quality. It's kind of a boring topic, but we'll try to make it interesting. And then Jack has a really fun story for y'all. So what is a, well, let me start out by saying, so we focus primarily on manufacturing pre-market exempt Class 1 or Class 2 devices that are non-sterile. That's kind of our wheelhouse. We look for designs that y'all design, and we kind of intend to operationalize them. That's kind of where we fit in this ecosystem. So that means that we're very focused on quality management, and so you're going to hear the term QMS a lot. QMS is a quality management system. In practice is basically a collection of documents and records. So documents tell you how to do a thing, records show that you did the thing. And basically, if you want to have a highly reproducible, safe process, you need a procedure for every operation that you do, down to a pretty microscopic level. And Quality is kind of seen as a roadblock to a lot of things. You know, hackers move fast and break things, and when you start getting into medical devices, you really have to slow down a little bit, but I'm a big believer in it being a thing that can be implemented with a kind of lower barrier and a more collaborative approach. So from the regulatory perspective, because there's kind of the practical perspective, you know, we're making things safely because they're going to our neighbors and our community. But from the regulatory perspective, it's a legal requirement to, you know, follow certain laws within your country. So in the US, that means Title 21 CFR Part 820 with about 30 asterisks behind that statement. You can ask me about those asterisks after the talk. It's kind of outside of the scope of this. FDA is kind of in a weird place. This February, they moved over to a QMSR, which is basically harmonized with ISO 13485. And if you know anything about ISO, you know it's very expensive. FDA kind of did a arguably shady thing where you can go to a website and view ISO 13485, but they make it intentionally extremely frustrating to do so. I always recommend we buy our ISO standards because you're supposed to buy your standards. We buy them from the Estonian standards of measurement and technology. You can get them for about 20 bucks as opposed to 250 bucks elsewhere legally. Yeah, so, you know, give that website a perusal. You can get the ISO standard that teaches you how to brew a cup of tea. All right, so where do we fall in QMS as an open source system? And that's really what we're trying to help with. And we're very fortunate in that we're not the first people to think about this or do this. We are in the early days of this because a lot of people haven't implemented these. So Tidepool is a 501c3 that kind of came out of the Looper community. They produce software that bridges the gap between insulin pumps and continuous glucose monitors. It's something that was kind of done in the shadows for many years, you know, within hacker communities. They brought it out of the shadows. They got FDA registered. They have an open QMS specifically for software as a medical device. I'd highly recommend taking a look at that. It's online. And also they're just wonderful people. You can email them and they'll talk to you, and they're nerds because, you know, they'll just talk to you about quality all day if you want. We also partner with a group at the top there, Open Source Quality Assurance System. We all use acronyms, so it's known as GOSQUAS. And they use they publish a system. Victoria's here. She's a product owner of GDT, which is Global Distributed Tracking. This is kind of a tool that we can use to implement our quality management system. It's basically a pseudo-anonymous tracking system. It was developed for use in aid distribution so that you could distribute aid with unique tracking ID, but it wouldn't be able to be traced back to the source. We use it in quite a few areas of our quality system. All of our tools have GDT tags on them so that we have a permanent record that can be used if there's an audit so that people can see, okay, you did your preventative maintenance, you know, oiled the machine, etc. And then we also use it for defect tracking. So we exceed FDA regulations in that we have a unique serial number on all of our tourniquets. And we do that so that we can track defects to the tourniquet level. I like to say that we practice what's called quality in depth because we have things like volunteers and it's a little bit chaotic. And so we go a little bit above and beyond and have redundant quality approaches. Let's see. Oh, and yeah, I guess that's our intent, is that we hope to bring an open source quality management system to the table for anybody that wants it. And maybe I'll talk about kind of where we started. So we started pretty scrappy. You know, we had all these Alice in Wonderland tags on all of our steps. So each of these boxes were a discrete step, you know, glue me, round me. And that's how we did our workflow. And we did inspections as we went. We produced safe equipment. We did actual testing at the end. But since then, we've built up our quality system, and I wanted to show kind of our embarrassing start, because it's okay to start small. As long as you can validate the design that you're making meets or exceeds the clinical applications, then it's okay if you kind of have a weird system. And I guess maybe I would mention, so another person or another group that I forgot to mention is Open Regulatory. They provide an open regulatory framework for MDR and FDA and a few other regulatory bodies. And I think those are really good starting points. Tide Pool is a great starting point. Open Regulatory is a great starting point. But quality management systems aren't the documents in your system. It's how you operate day to day. They need to be lived in. And so the second, you can spend a lot of time downloading, a framework and typing it up, but the second you make your first device, Murphy is going to come into the room and everything is going to go to hell, and so you're going to develop your own. And so, use ours, look at ours if you're interested, but you're going to be making your own regardless. Nope. All right, so open source everything. We're trying to commit to using and making everything open source. We have a very lightweight QMS. It's about 20 procedures long, nothing too bad. It was designed by some incredible volunteers, one of which is our second ever quality specialist, Dora, sitting right over there. Dora has a hell of a mind for system design. She'll talk your ear off, and you'll learn something very interesting. Dora and I kind of wrote this framework and have started putting it into practice. So we are also building more tools. So, we get something frustrating happens, we build a tool, we open source it, we put it out. It may not be the best thing, but we have checklists that we used to fill out by hand, which Jack will talk about more in a little bit. And now they're mostly digital and they're automated workflows, and all of this is on our Codeberg repository. And by all means, audit us. And if you find something wrong, my favorite type of feedback is when somebody says that I got something wrong in the quality system. I love getting that. So be brutal. We'd love it if you audited us. Okay, so Jack is going to share a story. This is a specific part of the QMS. We wanted to make sure that we spent some time where y'all could learn a little bit about how a quality system actually works. Part of the quality system is what's called a CAPA. A CAPA, and we love acronyms, a CAPA is a corrective and preventive action. And that is a formal process where you identify an issue, so you need to be able to see the signal. You investigate it, so you find the root cause. You correct it, meaning you isolate non-conforming material, you prevent it from getting out into the public, or you recall it. And then you fix any immediate issues, and then you prevent the issue, meaning you implement systematic or design changes, and then follow up to ensure that it doesn't reoccur. That sounds very complicated, but I think Jack's got a very interesting story, and this is kind of our, it's kind of a harrowing story, but this is our commitment to open source. Every mistake we ever make is on our Codeberg, and you can read it fully. But, thanks, Jack. You want the walking around, Mike?
This is fine. To get into sort of a practical application of the CAPA process and our quality system generally, I'd like to talk about CAPA 3, which we experienced in March of this year. It was at the end of one of our Wednesday work days. This particular day, we were doing lot 3 acceptance testing. So for every lot of tourniquets we make, between 250 and 500 tourniquets, we do a statistically appropriate amount of destructive testing based on an AQL sample, which Alex assures me people in this room know what it is. I didn't know what that was. And this particular day, we were using the tourniquet tester that we use, which was designed by Dr. Liu and Dr. Pierce of University of Western Ontario, I believe Fast Labs. And it's a really ingenious little device that allows us to use a 3D printed shell, an Arduino, and a load cell to make sure that our tourniquets are reaching appropriate clinical pressure. So we do destructive testing on an appropriate amount of tourniquets every lot. This particular day, we were on the very last test of the day, and the windlass on the right snapped at dramatically low pressure, an unacceptable pressure, and a knowing, kind of terrified look passed between Alex, myself, and our collaborator Mike as we realized we were kind of in it for the long haul on this one. I'm sure most of you are familiar with 3D printing and 3D printed parts, but for those of you who aren't, we print all of our parts at 100% infill for DMDM, meaning that it's just a solid chunk of plastic. This particular windlass that we discovered was hollow, meaning it had an internal structure generated by the 3D printing program, the slicer. Yeah, they often do this to like save weight, save time in the print, save material. So somewhere down the line, a printer had defaulted to these settings, meaning we had some hollow windlasses in the mix. So with the snapping of that windlass, we had identified the problem. We had a big problem. We had some hollow windlasses. We then moved to our investigate step of the CAPA process. And this is where we got lucky with the printers that we were using. The printer that we use keeps a video. I'll back up a second here. There was a little bit of foreshadowing here because this is the video that was found. We watched every single video of every single print that we've ever done. And we're able to narrow the problem down to this tray. So having satisfied the investigate portion of the CAPA, we moved to corrective action, which was 100% inspection of every tourniquet, every windlass in our workshop until we had found all of the parts. And you can see, thanks to a blurry, completely unrelated photo shared between two of our collective members, and this identifying smudge right there in the circle, we were able to limit the problem to lot 3. We had been testing lot 3 before it went out in the world that day, and this picture being the last box of lot 2 and having conspicuous windlasses proved to us that we were able to isolate the problem just to lot 3, which had not gone out. We knew that lot 2 had not been affected, which was a real relief. So having isolated the problem, identified, investigated, and corrected, we moved to preventative action. So now the way we handle our 3D printed parts is we implemented a 3D printed parts weigh-in system where volunteers clean and inspect parts, make a count of those parts, and we invested in a counting scale so we can check if there's any variation in weight and make sure that the parts are all solid. We also directly insert G-code to our printers now to bypass those presets that the printers are wanting to do to make lighter, worse windlasses. We also made some changes to our checklist design. You can see on the top right, that's our old checklist where we keep track in hard copy of all of the work that's been done to a particular box of tourniquets, a subdivision of our lot system. And with the redesign, we have really prominent lot and box number labels, and we're also including a novel 3D printed part ID number. So every part, like every printed tray that we get from our suppliers, including Alex, has a unique ID number that we can then narrow problems down very quickly to a very small number of tourniquets. And this is the digital copy of that checklist, which exists in our live dashboard. One of our contributors, Mike, has been working for a long time and recently launched our live dashboard built on top of GDT that keeps track of the actual work happening and what step each box of tourniquets is at in our system. So it's just the digital corollary to that physical checklist. Yeah, and to just close out, on a personal note, I think I don't come from a quality background personally. I come into DMDM as a sewer and a tinkerer and a maker generally. And I've been impressed that by how accessible this quality system actually has been as a codification of a fairly intuitive progress. It seems just a way of marking down a process that a group of people with a shared goal and a high standard of work can move through to address problems as they come up. So I think that quality management systems can seem really impenetrable and really like academic and really scary. At least they did to me with my background. And as we've gone through these CAPAs, I've just felt that they are, yeah, more and more accessible all the time. And I think another final note, just we as DMDM, we work with a large pool of volunteers, so we have a lot of hands touching the work. We train people that come to us without a background in manufacturing, without a background in engineering, and we hold them to a high standard of work with our quality system. And I think that you can view this as a tension between two opposing forces, this like accessibility of volunteers and sort of the austerity of a high measure of quality. But I actually don't think that is the way I would like to frame it. And I think that it's actually two parts of the same approach that is helping us make DMDM as we go, which is collective, collaborative, and transparent action. So we move together, we work together, and we're transparent about any problems we have along the way. And that's what allows us to integrate a lot of volunteers and maintain a very high standard of work. And that's the name of the game for DMDM, and hopefully that's the part that can scale and be helpful for other groups and other projects. And here we have some codes for our site and our QMS system. So thank you so much.
Thank you, everybody. We're going to have a 30-minute break, and then we'll join back here in just a few minutes. All right? Thank you. Down. 5, 4, 3, 2, 2.5. Okay, let's see. All right. Well, I brought you back, but I got to make sure I got this shared properly. Yeah, I think it's right. Oh, they're texting me. Okay, we're live, and it looks good, I think. All right. So, let me introduce Dr. Eisen. Caro Chassin is a regenerating composition of cells that produce a woman, an animal whose patterns of migration are not based on seasons, but rather chance, chaos, and opportunity. She is an artist and a professor of research at the John Seeley School of Medicine at the University of Texas Medical Branch, where she leads the medical prototyping lab. She holds a BFA in sculpture from the University of Houston, a master's in fine arts in design at Parsons, and a PhD in human informatics from the University of Tsukuba in Japan. Welcome. Oh, I did it wrong. I did it wrong. Okay, hold up.
Okay, so I don't get to see him down here. You want to expand that?
Yeah. Okay, there you go.
Wait. What happened?
Oh, did I move your speaker notes?
Yeah,
Guilty. There you go.
but you can't see it.
Oh my goodness. Okay, now we're.
Okay,
No?
is it? No.
It's one of these tabs.
Aww. How to make a family? No.
Yeah.
An open source family. Hey, that'll be a workshop.
I just got to make sure that the notes
Hey,
are.
stop. They
Okay,
can't
all right,
touch
fine.
any more things. Okay. Hi, how are you guys? I hope a little bit lively, even though it's been a long day, but it's been so informative and beautiful. So thank you for sticking it around for me. And today I'm going to present work that my students and I did, which is a bioreactor for creating tubular biofilms. Okay. And I want to start by thanking OSHA and the National Science Foundation for making this possible. This is a historic moment. It's the second conference at all for open source healthware, and we hope it continues with y'all's support beyond all the fabulous funding and amazing hotels, and we can still brave it through when we have to hang out under the bridge wherever it's going to be next time. And of course, the inauguration of the certificate, which was this year, and we debated and discussed heavily the last year and how to culminate. And I know it's still a work in progress. And so hopefully, actually, some of this presentation may inform that certificate as well. So I run the medical prototyping lab at the University of Texas Medical Branch, and it is
an interdisciplinary space for collaboration, materializing ideas, fabrication, creating simulation models. We do a lot of that for both clinical and medical education, and conducting research across all medical sciences and practices. At the University of Texas Medical Branch, we are the first makerspace inside of a hospital in the US, and we were put together by a company called Maker Health, which was a spun off out of MIT, and actually the nurses at the University of Texas Medical Branch. So we're really proud of that, and we hope that, you know, we continue being a clinical space rather than an educational space. It's usually the natural place for a lot of these prototyping labs to live in education, but we know that we've made a great impact in healthcare. These are some of my students. I just wanted to put some faces for you guys to see the rest of the lab, and we serve all walks of life in our institution. We have nursing, of course, pathology, ophthalmology, anesthesiology, radiology, School of Medicine, School of Health, professions, School of Nursing, Graduate School of Biomedical Sciences. We also have the Galveston National Lab, which is one of 2 BSL-4 in the country, which means that we work with Ebola or Zika, high containment pathogens. And we're also the TDCJ, the Texas Department of Corrections hospital. So we see all the inmates, prisoners from Texas. And we have many other labs as well. Aerobiology we work with a lot as well. And so, yeah, it was put together by Dr. David Marshall, who was the chief nurse officer. And this is me. I'm assistant professor of research in the pathology department and leading the lab. And my background is in bioart and bioengineering device art. I'm kind of a reverse bioengineer, if you may. And really, my goal has always been to bring, you know, the intersection of art and science to the real world, and allow for art to be a contributor to science rather than just an illustrator of science as we usually see it. Some of these, this is what we offer at the lab. We iterate material processes for clinical support. Sometimes people buy the wrong stuff and we have to 3D print something to make it work. Sometimes, you know, that turns into a whole new project. For example, our nurses are now working with Lazy Boy to reformat some of our recliner chairs for patients. So it sometimes turns into, you know, a makerspace device that then informs industry standards. So they're recreating the standards for chairs inside of patient rooms to make sure that they have a hook for the Foley bag when you get a Foley catheter. We also materialize 3D imaging. So 3D imaging, 3D printing as clinical imaging is really prevalent now, and actually insurance covers it. So for all of you that are interested in implementing 3D printing in clinical settings, there's an opportunity for it to actually be rolled up into the awful complex that the American medical insurance system is. But hey, you know, it can get covered now. And so that's one of the things that I'm implementing currently is surgical simulation models or surgical planning models, so we can 3D print CT scans for surgical planning. And then we also generate multiple anatomic models or devices for supporting education, and so it's also simulation. And essentially, we do prototyping, which all of you guys are very familiar with. And this is a map that I like to share about the innovation process within within our institution and kind of in general, I would say, you know, we invent, and then from inventing we test, and then we propose clinical studies after we have done sufficient bench or animal testing, and it goes into human research, which is governed by the institutional review board that functions as an arm of the FDA in a way, to make sure that proper ethical review is conducted, and consent, and all of these beautiful trainings that you may have if you have to do human research for clinical sciences. And today I want to present specifically on surgical suture simulation models. A lot of them are models. Can I take this off of this? Oh, yeah. Okay. Models that are essential for procedural. They lack realism a lot of times. And sorry, I had my notes are like mixed up. So a lot of times we'll see that these models are, you know, not realistic enough, or the materials that we're using is, for example, silicone. And so we've been using bacterial cellulose, which it's kind of a fancy way of saying the mother of kombucha, for example. Maybe some of you guys would understand it better with that lingo. But we actually were just using bacteria, not the SCOBY, which also has a symbiotic relation with yeast, but also, and so therefore creating more realistic tissue with better tensile strength. Oh my God, this is all messed up, Avinash. The thing is that my notes are separate from, like, I think that's not even, oh, where was I? Okay, I got it. Never mind. Okay. So sorry. So our cellulose produces a multi-layered, I guess, medium for surgical simulation that's a lot more realistic. And so the strains of bacteria that we use are Bacillus amylofaquations, Bacillus subtilis, and Bacillus velezinensis. And here you can see one of my students cutting up into one of the first batches that we grew, and it's really meaty. And we also did tests where we fed it coconut water and beer, and we were just like, yeah, let's throw things at the wall and see what sticks. And we ended up with a protocol where really we just fed it tryptone, which is a pre-digested protein, and so it's a lot shorter chain, and so the bacteria can eat it and therefore create much meatier cellulose faster. And as you can see, as it grows further and further, it changes consistency into a much more kind of smooth, layered cellulose here on the bottom. And we incubated at 30 degrees centigrade. Yeah. And here you can see how it grows in about a month. I mean, a week. And you can see our students suturing it. So you can see it's a lot meatier, and so it has these fibers, and it's not like a uniform material like silicone would be. So it's a lot more realistic, and the fact that it's also wet, even though it's not blood, it's just, you know, clear liquid, also allows for the students to have a better feel for the tools and when they're actually going to suture. And so then after you suture it, you put it back into the brine and it heals like this. And so we created regenerating suture models that heal. And so after you wound it, suture it, it heals back and you can take up the sutures. And so that was great. We presented that at the American College of Surgeons and people thought it was pretty great for practice. And then we decided to figure out how to create tubular models so that we can recreate vessels simulations. Vessels are really hard to suture, as you can imagine, so a lot of surgeons need to practice this specifically. And so for that, we created the tubular pellicle forming bioreactor, which is a rotational air liquid system enabling 3D biofilm formation. And so you can see it here. It's very simple hardware-wise. It's just a geared motor that goes continuously. And it has a straw that rotates, and we've put some grease. If you have any questions about how to keep it waterproof when you have a motor, you just use grease and you make a motor waterproof. And so you put it at the threshold of the culture medium and the air, and the oxygen allows for the pellicle to form. And because we sanded the straw that we have here, the pellicle catches, and then it just kind of rolls and grows around it. And here you can see our patent drawing, and we, of course, didn't file a patent because this is an open source conference, but we are required by the university to submit an invention disclosure form, and then they decide whether they can make money off of it, and if they can't, they often release the technology to us, which we have done. And so the culture grows and between 28 and 30 degrees, and with the oxygen, within 7 to 28 days, it grows the tubular cellulose. And so we have achieved consistent tubular geometry and a multi-layered fibrous architecture. It has high flexibility. Actually, the structural integrity is not that great. I think that if I went back to add more structure, I would maybe perhaps put some sort of mesh as well at some point, maybe just like gauze or something very simple. And yeah, we've achieved, various thicknesses, but 1 to 2 centimeters is ideal. And so I also wanted to put this for this conference specifically because we're talking about intellectual property, specifically of medical devices. And so I wanted to put the release of our technology here for you guys to see and maybe document this presentation for your certificate. So the university has released this technology to us as the inventors. We acknowledge the receipt of Dr. Chassine's request for a release of the invention listed above. Present the invention at the 2026 Open Healthware Conference, which is sponsored by the National Science Foundation. The Office of Innovation and Commercialization of the University of Texas has considered the board's interest in the invention and determined that it is in the best interest of all parties to release the technology to the inventors. We concur that this recommendation, that the UTMB does not assert and exploit the board. Exploit, you see this language? I really wanted to show you guys this specifically because I guess this is what the conference is really about. Yeah, and so here are the terms. So we have to allow the UT system to use it royalty free, which, you know, now that we're open sourcing, anyone can really. But if we make any money off of it, aka the 3 listed inventors, we have to pay the university 10%, but you don't. So don't maybe pay me 10%. I don't know how we could do this, but you know, I often think about how does that work? Why is it that the inventors get penalized if we were going to open source something for the commercialization of property? So it's really interesting. And then the number 5 is really important. In no event shall the university be liable. Avinash, this is like for the certificate, right? For any use of the invention by the inventors or any third party. Inventors shall indemnify, defend, and hold harmless university and its board, aka OSHWA or whatever, like replace with OSHWA here. Regents, officers, directors, employees, and agents from and against all damages, costs, and expenses for any loss, claim, injury, or liability of any kind that may arise from the commercialization, transfer, use, manufacture, or sell of the invention by the inventors of any licensee or assignee thereof any third party. So yeah, and in all caps, inventors understand and agree that the board and university makes no representations or warranties of any kind, express or implied, including without limitation as to the invention or as the operability or fitness, I know, of any use or particular purpose, merchantability, safety, efficacy. I mean, you know, provability by regulatory authorities, time and cost of development, patentability, and or breadth of invention, absence from the rightful, I mean, you guys know how to read. But yeah, I thought this was probably going to be the most important part of my presentation here, and I hope that OSHA can use this language to make sure that your certificate makes clear that you're not liable, and also that you're not guaranteeing any safety or review, and that you're solely reviewing for the intellectual property of it. So with that, I want to say collaboration is the basis of knowledge, and I feel like mutual admiration is the glue for trust. And if you have any questions, this is my email. Feel free to reach out, and thank you very much.
Thank you. Yes, that is really helpful. If we use that, will UTMB sue us? All right. Is it open source? Yeah, I don't know. All right, now pray for me, everybody. I've got this one's pre-recorded video, so let's see. All right. Oh. Okay.
Hi, I'm Joel Murphy. Hi, I'm Joel Murphy, and I've been working with and making open source hardware for over 20 years. I've been a supporter of OSHWA since its foundational meetings in 2010. I was a board member for the organization in the teens, and I'm honored to have been industry mentor for their NSF I-Core training in the fall of 2024. I'm sad to miss you all in person, but I'm super happy to share this story with you. My background is in visual art, and I made kinetic sculpture for years through the 90s and aughts, but that never made me any money. In 2006, I got lucky and had an opportunity to apply for and got a job teaching physical computing to Parsons Design and Technology grad students in New York City. I was an adjunct professor there until 2014 when I burnt out. During that time, I started up my consulting company called Flywheel Lab, where I make other people's cool projects. When I started teaching, it was a couple of years before Arduino had a stable hardware platform. So in order to give my students the most comprehensive education, I went low level with microchip PIC chips, which kind of pissed off my students. But by 2011, Arduino was firmly in place as the go-to platform for learning and building projects with electronics of the size and scope that my students worked in. That spring 2011 semester, a number of students wanted to incorporate biosensing in their projects. As far as biosensing goes, there's some low-hanging fruit, like galvanic skin response, now known as electrodermal activity, but a few intrepid students wanted to get heart rate data to play with. So I dug around and found a fairly simple circuit using an LED and an op-amp, components that had already been a part of their earlier lessons. The circuit is called a transimpedance amplifier, or TIA, and it is the core of a photoplasmograph, or PPG heart rate sensor. I gave my students the schematics and guidance, but still, the breadboarded projects barely worked if you held your tongue at the right angle. After the semester, I met up with my friend and colleague Yuri Gitman, who was also teaching physical computing, and we figured if we could make a functional PPG sensor, we would have more cool projects and less sad students. Our classes were always hungry for new sensors that were easy to use and gave a simple, direct signal. We had seen the burst of startups rise up around us over the previous couple of years, and we're trying to figure out a way to break into the open source hardware scene with a viable product. So we put this idea on the top of the list. That summer, we spent 2 months and about $250 prototyping what we called Pulse Sensor. Those were the heady days of crowdfunding, and at the end of the summer, we launched a Kickstarter campaign to raise funds to make and sell Pulse Sensor to folks who wanted it. Having working prototypes and contact with a known manufacturing partner in Shenzhen lined up, we lowballed our funding goal, setting it at $5,000 to cover a 500-unit run and pay ourselves a little bit of scratch, because we wanted to succeed, but more because we wanted anyone who wanted a pulse sensor to get one. We had tapped all our networks to get eyeballs on our Kickstarter, and new folks wanted it. We wound up getting $18,418 from 491 backers. Do the math. Since then, people keep buying pulse sensor, and so we keep making them. Our company, called World Famous Electronics, is small but sustainable and has run a profit for the past 14 years. The title of this talk is Designing Sideways, and that's what I did when I was working out the hardware prototype for Pulse Sensor. I looked at the TIA circuit and the issues involved in designing it with frequency-matched components and tuning it with just the right passives, and thought, there's got to be a better way. I'm a sculptor, so I'm lazy, and I always try to either cut or look around corners. I searched around for what kind of component solutions were available and discovered that Avago made a small integrated light sensor chip that goes inside every mobile phone to measure the ambient light so the MCU can adjust the LCD brightness. It has a tuned photodiode TIA circuit in it that has a peak sensitivity to green light, 515 nanometers specifically. With that sensor on the bench, I just had to find the right green LED, and turns out King Bright happened to make a reverse mount super bright green LED. The two parts are frequency matched almost perfectly, and I don't have to tune or tweak anything. The reverse mount LED is especially applicable because that means the only thing on the front or skin contact side of pulse sensor is the tiny Avago chip, making it easy to cover with a small, round, clear vinyl sticker to protect it from skin oils and sweat. This is a picture from our Getting Started guide about how to apply the vinyl sticker that comes in our kit. At first I thought green, that's a bit weird for a heartbeat sensor. I thought red would be better, and maybe it would hurt our Kickstarter campaign or future sales. But I think it hasn't hurt, and I hope it turned out to be more of a pulse sensor trademark green. It just so happens that in 2015, a few very successful pulse sensor sales years after our Kickstarter campaign, Apple came out with the first generation Apple Watch. And what do you know? They used a green LED for their PPG. This is the waveform from our first pulse sensor, the one we delivered to our Kickstarter backers. It shows a classic PPG pulse wave riding on a slowly drifting DC level. That's totally legit and really cool, but it's not easy to tease out the heartbeat from this signal in software, especially with the 10-bit ADC in the Arduino Uno, and especially with a sculptor trying to do digital signal processing. So in the first half of 2012, I learned about and developed a hardware high-pass filter to clean up and amplify the pulse sensor signal. This is the output from the filter I designed. The green line is the voltage midpoint plotted as a reference, and the pulse sensor signal is in red. The clean, bright pulse wave is super easy to run a simple algorithm over to find the heartbeats. We provide comprehensive Arduino software library with examples for many applications and hardware platforms. And since it's just an analog signal, you can use any signal processing scheme you like to derive heart rate data. World Famous Electronics has not published any validation of our software output against any third-party PPG or ECG. We have said from the beginning that our pulse sensor is for entertainment purposes only. Internally to the company, we have tested simultaneously pulse sensor and our software alongside commercially available heart rate monitors and have found that our algorithm results fit well within the BPM ranges of the standard. In just over a year, Yuri and I went from concept to working prototype, acquired seed funding based on working hardware, then bootstrapped our sales to further develop the hardware and software to make a finished, successful product. Here you can see the pulse sensor kit parts. It comes with a 24-inch cable, Velcro dots and strap, vinyl stickers for protection of the skin contact surface, and a size-matched costume jewelry ear clip for ear-worn applications. We recently added a TPE printed stabilizer ring to help reduce movement noise when worn on the finger. We have a thorough Getting Started guide, a well-maintained Arduino library, and over 25 examples and tutorials. Our website is regularly updated. In 2023, we published a book with A-Press that collects best practices and project starter tutorials. Since 2012, in our busiest years, we have made and sold 6,000 pulse sensors, and in our slowest years, we've made 3,000 to 4,000. That makes for somewhere around 70,000 pulse sensors in the wild. Now, I have a personal rule goal that states, do not make future garbage. And that is one of the many reasons why I was attracted to open source hardware in the first place. Making pulse sensor open source ticks that box by saying, take this thing and see it as an opportunity. Use it as intended, mod it, or use it for something completely different, so long as it's useful and used. After having sold so many pulse sensors for so long, it's hard to know just who is doing what with them. But some stories stand out. The one I'm going to tell you now has been waiting to be told since 2013, and it fits well in this conference. Back in 2010 in New York, Maker Faire held their first World Maker Faire in the parking lot of the New York Hall of Science in Queens. And the fairs ran annually until 2019. Those first years were crazy good. And through 2016, I managed to man a booth there promoting Pulse Sensor or some other open source hardware project that I was a part of. At our pulse sensor booth in 2013, I met Murtada Al-Tamimi, an Iraqi who had been traveling between Vancouver, where he was in school, and his home in Baghdad over the previous year. The Iraq war officially ended in 2011, but they were still suffering from limited resources and infrastructure. In the summer of 2012, he and some friends were starting a Baghdad hackerspace to foster innovation and open source solutions to the problems Iraqis were facing at the time. They called it Fikra Space. Fikra means idea in Arabic. In 2013, the hackerspace was growing, but still suffering from limited tools and supplies to make things. He told me a story about his experience with Pulse Sensor, and I want to share it with you here. The following is from a doc Murtada wrote and some images that I could find from the Fikra space. The friend he mentions is Bilal Ghalib, one of the Fikra founders, who I believe is the one sitting in this photo. Here is Murtada's story in his own words, only edited for flow. The story of heart monitors in Iraq began when I stumbled upon a project that Bilal made on Instructables about his recent visit to Baghdad. He talked about his experience with the TEDx Baghdad team and the workshop he held to introduce them to the open source technology. And it was in one of those paragraphs that my eye caught the word Arduino. And so I got really excited and was hoping that he was talking about the same Arduino MCUs that I came to be familiar with during my last semester at school as I worked on a project that relied heavily on using an Uno. At first, I had no idea and thought to myself, what are the odds he's talking about the Arduino MCUs? The post had open source technology in its title, and for some reason, I always thought of open source stuff to be strictly software. And so it seemed to me that the Arduino as a piece of hardware don't really have a place in that blog post. But then I got really excited when I read further and understood he was talking about the very same Arduino technology I was using back in school. So as soon as I finished reading that lengthy blog post, I clicked on the little +BG that Bilal had left at the bottom of the page as a signature, and I was directed to his Facebook profile. I rushed to click on send message and started writing him what came to be a fairly lengthy message that was overly polite and apologetic. I felt the need to apologize in case he didn't like people he didn't know sending him messages on Facebook. He replied back saying, "Beautiful message, let's talk soon." This happened exactly 10 days before I was leaving Baghdad. I had been there for a quick visit at the beginning of the summer to see my family. It took a couple of days until Bilal and I actually managed to talk because of the time difference, which he didn't even realize since for some reason he was thinking I was still in Vancouver, even though I explicitly mentioned in my message that I was visiting Iraq and would really love to help put those Arduinos he left behind to good use. "Holy shoot," Bilal screamed with excitement when he realized I was in Baghdad, and we started discussing ways I could help. He explained that the devices, one of which being a pulse sensor that was donated by Pulse Sensor, were given to the TEDx Baghdad team and could be assembled together to build a heart rate monitor. We wrapped up our Skype call, and Bilal promised to connect me with the people who are holding on to the devices. And so he did. But it took a couple of days for the back and forth communication to actually lead to a meeting with the members of the TEDx Baghdad team who had the Arduinos and heart rate sensors. That meeting took place exactly 2 days before I was leaving Baghdad. So I wasn't sure how much I was going to be able to do with the prototype with the time I had left. But I went home that evening and tried to set up the Arduino with the peripherals, and much to my surprise, I was able to get a really simple and primitive prototype working by simply following online tutorials and instructions that came with the parts. As soon as I was able to get things working on my computer, I sent Bilal a message saying that I got something simple to work. He got really excited and asked for photos, so I took the picture above. He was at a conference and told me to quickly send him a photo as he was going to go up on stage and talk about this. It took a while for the photo to upload over the slow internet connection I had in Baghdad. By the time Bilal got it, it was too late to show in front of his audience. Here is an excerpt from the messages we exchanged over Facebook as this happened. As I read this and look back at it in retrospect, my favorite part of this conversation is Bilal's line, "It's the start of maker culture in Baghdad, man, not the end." This was taking place around 1 a.m., my local time, but I wanted to keep improving the prototype. I played around with the tools more and messaged Bilal about my progress. He responded, suggesting that I should connect with the Iraqi doctors who worked on the TEDx Baghdad team and ask them about the environment and requirements they had in mind for this device. So the next morning, I called Dr. Anas and told him that I managed to get something to work. He got really excited and told me that this would be very helpful. He said this to me using English words himself. Believe it or not, our hospital doesn't have a functional heart rate monitor. I discussed with him the possibilities and features I could implement, mentioning that it's easy to build something that graphs the heart rate of the patient over time and sends the doctor an SMS or email if the heart rate of the patient dropped below a certain threshold. Dr. Anas explained that such a thing won't be practical for their environment because they were looking for a portable device that is battery operated and can work without internet or computer. He said even something that simply has an LED that flashes with the heartbeat would be useful. But I knew I could do better with the tools in the inventor's kit provided by SparkFun. There was an LCD, so at the very least, I could display the instantaneous heart rate of the patient. There was also a small buzzer, so I thought I could use that to sound an alarm when the heart rate drops below a certain threshold. But what should that threshold be? I wasn't a doctor. I had no idea. And I assumed it might even be different for every person and is something that is determined on a case-by-case basis. So I thought it would be helpful to have that threshold configurable by the doctor instead of hard-coding it in software. There was a handy potentiometer included in the kit, so I decided to use that for configuring a threshold. The kit also had an LED, so I decided to throw an LED on it that fades out with the heartbeat just for fun. There was a sample code for that provided with the online tutorials on pulse sensor. So that was the prototype I had in my mind, but I had less than 1 day to build it with minimal tools. I knew that I had to give up sleeping on my last night in Baghdad, but I still wasn't sure if that was going to be enough time. I started scrambling whatever tools we had around the house to start building the device. I managed to find a soldering iron, but no solder. So I asked my brother to buy me some from the closest hardware store. Then I realized that I needed some thin connecting wires, since this whole time I had been using those jumper wires that came with the inventor's kit and were easy to use on a breadboard, but wouldn't be suitable to use on a solder board. I looked around the house, but couldn't find anything useful, so I decided to go and look for some at the local hardware stores. I knew it wasn't going to be easy to find what I needed, and wasn't even sure how I would explain it in Arabic, so every time I got into a store, it took a lot of words to explain to the person working there what I was looking for. And one of them had a really funny response as I asked for a single thin electric wires. He responded asking, "How many amps are you looking to drive through it?" I replied, not more than 500 milliamps. He seemed confused and thought I didn't know what I was talking about and said, "What? How far is the generator you're connecting to?" And that's when I realized that he thought I was looking for those single cables that people were using a lot to connect to nearby AC generators that became popular in Iraq to compensate for lack of electricity on the national grid. So it's a usual practice for store owners to ask about the amount of power someone was looking to draw and the distance of the generator in order to be able to give the cable with the necessary power rating. After visiting at least 10 stores, I eventually managed to find some wires to use on the solder board. Electricity was a problem, of course, so I wasn't able to solder parts whenever I wanted. I ended up staying up until 6 a.m. that night to finish off most of the soldering I had to do. There were still some final touches I wanted to do, but I couldn't keep my eyes open at that point. As usual, my last day in the country was hectic, but this time it was even more packed because of some family matters. Not to mention all the goodbye visits I had to pay to my relatively big extended family. And as I went from house to house, I took the inventor's kit and Arduino with me and tried to make some final tweaks. As my mom drove, I tried to pull out the blue box of tools to cut out some wires, and I still remember her telling me to put the stuff away as we got close to an army checkpoint so as not to be suspected of building a bomb with all the wires and electronics I had sitting in my lap. So after a pretty packed day, I scheduled a last-minute meeting with the members of TEDx Baghdad I initially met with. We agreed to meet around 8 p.m. at Everyday Cafe in Al Mansour, the same place we first met. But I explained that this was going to be a quick meeting since I still had to go back and pack. Dr. Anas couldn't make the meeting, but I ended up meeting with another member who worked at a hospital too. I showed him the prototype, and he was pretty excited to see it working. We discussed different possibilities of improving it and expanding its functionality, and he asked if I could give him some pointers if he wanted to hack around with the software to introduce new cool features. Before finally handing it off to him, I thought of Bilal and how disappointed he would be if I didn't take photos of the prototype. So I pulled out my iPhone and took a few shots and a video with the device in action. This is the shot he took. Unfortunately, I don't have the video. Pulse Sensor has directly led me to the development of other open source medical adjacent devices, but those stories will have to wait for another talk. I'll just mention OpenBCI, which has began as a DARPA SBIR grant funded by the Obama Brain Initiative in 2013, and Timpan, an open source hearing aid development platform funded by NIH and the National Institute of Deafness and Communication Disorders. If you want to learn more about the history of Fikra Space, their Kickstarter campaign page and updates are rich in stories, photos, and links. As far as I can tell, they closed in 2020, but may have regrouped as some other entity since then. Here's a link to their crowdfunding page. Also a link to my website, biomurph.com. You can find me on most socials as @biomurph, although I am not super present on them. Thanks so much for the opportunity to share my and Murtada's story today. I hope y'all are having a great time, and I'm sure I'll see you again in person soon. Aloha.
And Joel wants us to know that he's on Discord. If you have any questions, you can shoot him a message. He's available right now. Okay, so I should also remind y'all as we're getting ready to close out with our last talk that tomorrow there will be a closing reception at Open Water at 7 p.m., 733 Front Street. And there'll be a reminder about it tomorrow at the talks as well. We'd love to see you all there. And for our last talk, we have Ritwik Shandilia, who grew up moving through many different communities, shaped by a deep respect for public service and by seeing firsthand how people live across drastically different economic conditions. Those experiences made questions about access, especially access to healthcare, feel personal, practical, and urgent. He received his undergraduate education in electrical engineering and his master's from Cornell University, and has worked across systems engineering, hardware research, avionics, and early stage technology investing. Eclectic and deeply curious, Ritwik loves talking with people and hearing new ideas, and is happiest in conversations that reveal how differently people see, build, and move through the world. Welcome.
Hello, hello. Thank you so much for the wonderful intro. I know it's been a really long day. So when I was planning and sort of figuring out what to talk about, I just thought that I just try to make this as digestible as possible and not bombard you with a lot of information because you guys are probably already quite overloaded. So here to talk about OpenPST. And I'd like to start with a really simple question, which is, how do you measure the return of a feeling? Now imagine you guys are holding whatever you have next to you. It could be your phone, it could be a pen, but you can't feel that anymore. You can't sense that anymore. Just remember that feeling for a little while. I'll come back to it in a bit. So about a year ago, that's Michelle. Michelle, shout out to Michelle. She is the collaborator on this project. So about a year ago, we were just wrapping up on a project called Helia, which also a medical device, which was addressing osteoporosis in women. And so we were doing some interesting work there, and we were just wrapping up when surgeons from Weill Cornell, they reached out to us and they're like, hey, we're doing some interesting research around sensory recovery, nerve recovery. And since you guys have already been working in this area for a while, would you guys be interested in this? So we're like, okay, let's see what's this about. And when they told us what they were doing, it was pretty exciting. So so the work was being done out of this lab called Otterburn Lab, and what they were doing is that so Dr. Otterburn used to perform mastectomy on patients, but usually what happens during these surgeries, as you see those nerve endings there in the diagram over there, so during the surgery, usually those nerve endings get damaged and you sort of lose sensation. And when I first heard this, first it was kind of personal as well, because when I had undergone a surgery, I had also undergone something very similar. And it's really weird. It's actually really weird that you can't really feel anything, and you keep pressing, but you can't really feel anything. And sometimes it's really painful too. But what really sort of stuck with me beyond that was when they told me a story of a patient, a mother who had come into the clinic, and she told them that whenever she tried, she'd just undergone the surgery, right? So she told them that whenever she tried to hug her kid, she couldn't really feel him anymore. And that was sort of when it really hit me. I'm like, okay, this is something really impactful. Let's see how I can contribute here, how we can contribute here. So the main thing that they were working on or they needed help with, was fixing this really old clunky device. So this device, what is usually used for measuring how your sensation at different body parts are recovering over time. So you can quantify how much pressure you can feel. And so the major problem with this device particularly here was that it had gone out of production, right? It had been a few years. It had gone out of production. It was, one of the things that the clinicians told us is that it really wasn't, I don't think people thought about how people might be using it or how doctors might be using it, considering the ergonomics of how that device is and how you hold it. It was clunky. And I think beyond that, I mean, imagine this. You see that briefcase, that huge suitcase over there? This entire thing comes in this really big suitcase. And inside that suitcase, the company had even upsold like this tablet, so without which apparently you can't use this device, and which made no sense to me. But imagine this: you're a patient. You're just gonna go and get a checkup. You're in this very vulnerable state. You know, you can't. You're really exposed and very vulnerable, and you're just sitting there. And the doctor walks in with this really, really big suitcase and opens it and takes out this really complicated machinery here. It's quite overwhelming. So we decided to fix this. We were like, let's see how we can fix this. So quickly, how this usually works is the yellow part that you're seeing is the chest or the contour, and the small part, that's the device. That's a sneak peek into what we built. So you take the device, so the curved end that you see, it's called a prong, and you take the device, apply pressure at different pressure points in the contour, and it's like applied perpendicularly. And the patient also has a button in their hand. So whenever they feel any sensation, they just click, and all well and good. So this is what it looks like. This is what the doctors usually do after they get that data. They divide the breast region into different parts and regions. So you'll see here that's pre-operative and pre-op and like post-op. So at pre-op, you see this 100% sensation. They haven't really lost any sensation, but even after 3 months, they've almost lost half of their sensation. And over time, because of, let's say, they do nerve regeneration surgery, the doctor that we were working with is one of the few doctors in the States who can actually perform this one dual neurotized surgery. Don't ask me how it works, but they perform this really specialized surgery, which has shown really good effects. So here is actually that when compared to like a normal recovery of say 50% or 60%. But yeah, so the idea here really was to help them quantify and measure how effective the treatment has been and how the progress is being made and how the patient is recovering. So we started prototyping stuff, and it was pretty ugly at the start. But the idea here really was that we wanted to design and solve problems from inside out rather than outside in. We wanted to work with the clinicians themselves and see what works for them and what doesn't work for them. So from the top to the bottom, the first one is probably like the earliest shell design that we had. It's still quite clunky, but it's moving into the direction that we hoped for, which was something that's more natural to hold, something that's more flexible, that your wrist is in a much more natural position. Like some of our inspiration really were like water picks that you have. So it's like very natural. You can maneuver it around really easily. And towards the end, that was like one of our final prototypes. That's Dr. Otterburn, that's Michelle, that's Carson, his student. And they're trying and testing one of our first versions out here. You see the small button. And this was one of the earliest prototypes. And the interesting part really is that when you work with the surgeons and the clinicians themselves, you catch on to problems really early on. So for example, you see the cable there, right? So one of our initial demos that we did, when the clinicians were using the device itself, the cable was hitting the patient's chest frequently, again and again and again. And maybe we wouldn't really have been able to catch this on our own if we didn't have someone who's an expert at this. So there were many other issues like this. So for example, the final device ended up being like an extension of the arm itself. And again, this was done and designed in collaboration with the doctors and the clinicians. But that's like the old version, which is more clunky. And this is much more portable. But so how does it really work? It's actually quite simple. So which I think makes the impact even bigger. I think leverage that you can have with something so simple, it's actually pretty interesting. So like I said, if you remember the contour again, we have the contour here. We take the device, press it against the contour. When we press it, the prong there is connected to something called a load cell. Someone had already spoken about a load cell. And so what really happens when you press is the load cell sort of bends, and whenever that bend happens, it converts that into the electrical resistance in the load cell changes, which gives us some pressure and force values, which is then collected by the ADC there. And whenever the patient clicks the button, it samples those past few readings, and then that's how we sort of quantify it and then show it to the clinicians themselves. But it being open source, we had to really think about reproducibility here. We went back and forth that, hey, the original device had a very, very tiny load cell. So we were like, should we think about designing it on our own? Should we just make something in-house? But then we realized that not everyone's going to have the ability to do something like that. So we just went to Adafruit and just bought like the simplest one out there. And then we drilled a hole at the top. And for the prong, we just bought like a simple brass wire, used a jewelry kit, bend it, and just stuck it inside. And that worked fine. We actually got pretty accurate readings, and like the measurements were comparable to the actual device. So when we were done, how did it perform? So we were done with this about December last year, and in Jan this year it was deployed into the clinic. And I think this was a month or two in. I reached out to the clinician, and they gave us the feedback, and like you can see, it was pretty positive. And we got really good feedback, and I think it addressed a lot of our initial concerns, which were around providing a better care experience for the patients overall, patients feeling less intimidated going into the checkup, and it being very portable, very light, and very fast to use. They overall enjoy the experience quite a bit. But the downsides of building it or just 3D printing it sometimes is like the wear and tear is really unavoidable. So, I mean, 2 days back, I just met them again. I was like, let me just sort of get some new feedback and see how what's going on. So the button stopped working. The screws had come off. It was very, very janky at times, but that's good. I mean, they were really, really active about giving us feedback. They were really excited about that. And if you've been building products, you know that that is always good. That's really, really nice. And that just showed that they were actually using this, and this was really helpful to them. So that was the overall experience. And when I think about it, like how, in what ways can this be expanded? This was right now only for mastectomy, but this has other applications as well. For example, someone's undergone amputation, right? That particular region, very sensitive, very painful. You need to figure out ways to, quantify how the recovery is going. Stroke patients, and one of the other common ones is losing sensation in your fingers. That's super common. But addressing the elephant in the room, AI. Did we use AI? I mean, we did use AI, but it was actually pretty interesting. So because we were able to use AI, we did end up spending a lot more time with the clinicians themselves. We were able to sit with them. We were able to iterate a lot quickly, a lot faster. We were calling it demo-driven development. We were just demoing as much as we could. This was on calls. This was whenever we could. And I think the pace at which we were working and we were building, it would have been much harder to do it without using any sort of AI. So kudos to that, I guess. But I think the core idea still here was that the care experience was still decided by the doctors themselves, by the surgeons themselves, and not some AI or any arbitrary or hallucinated thing. But towards the end, like our entire team, we were left with one really big open question. Like, it's not just us or them who sort of are going to something like this where the device is no longer profitable. The device is no longer commercially, exciting for the company. What do you do then? And we were left with a lot of open questions. And I think going into the conference, it was basically just that we, like, how do you decide when a medical device and we're sunsetting a medical device, what happens to it, especially if it's of critical need? Should there be more opportunities or frameworks or policies which encourages collaboration between these private companies and say open source bodies to have a common framework which can help decide and help handle sunsetting of these very critical medical devices? So I think as I end the talk, like I promised, very simple, very digestible. I think I would urge all of us to really think about this as well, because this is still an open question, but I think this work that needs to be done here, and I'd be really happy to talk to any of you after this about this as well. But yep, thank you.
All right, that brings us to the end of our talks for today. Thank you all so much for being here. Yes, a round of applause to all of our speakers. You can find the schedule for talks for tomorrow on the website, and we really hope to see y'all again. Thank you very much.